The cryosphere is the ice mass of our planet, the ice sheets, permafrost and water ice of the poles. A moderator of ocean and atmospheric temperatures, a sun reflector, the cryosphere is an integral part of this planet's cooling system. Climate change is shrinking the ice caps, and it's a runaway effect. Our world is warming, the oceans are rising, and we need to do something about it. Of all the fresh water on Earth, 99% is stored in ice sheets, the large frozen masses that form over land. As climate changes, melting ice sheets can contribute to rising sea levels, which can place vulnerable cities around the world in jeopardy. From the South Pole to Greenland, from Alaska's glaciers to Svalbard, NASA's Operation Icebridge covered the icy regions of our planet in 2017, with a record 7 separate field campaigns. The mission of Icebridge, NASA's longest-running airborne science program monitoring polar ice, is to collect data on changing ice sheets, glaciers, and sea ice, and maintain continuity of measurements between IceSat satellite missions. World-renowned leading climate scientist and astronaut Dr. Piers Sellers was director of the Earth Science Division at NASA Goddard. Having seen Earth from space on 3 shuttle flights and 6 EVAs, Dr. Sellers was deeply concerned for the future of our climate.
Now, Icebridge is probably one of the most important field campaigns we have running right now. The world is warming, and it's warming faster in the north, around the Arctic, than anywhere else by a factor of 2.5. It's 2.5 times increase in warming here compared to the global average. So this is where it's all happening. And as a consequence, the ice is melting fast. It's melting on the Arctic Ocean, and the ice mass on top of Greenland is melting and falling into the Atlantic. So we're mapping that using aircraft and satellites where we can. And of course, we've got people on the ground checking against these data as well. So this is ground zero for global warming. We're doing a lot of work here. We put a lot of effort into it. And I think it's paying off in terms of improved understanding.
Operation Icebridge began in 2009 and continues to fly aircraft through the region with advanced sensing equipment and coordinated land traverses by scientists to ensure accuracy of satellite data. Now, in conjunction with the European Space Agency, they coordinate and share data with additional satellite assets which fly identical science instruments. Just why are the ice caps melting? Because of the so-called greenhouse gases, carbon dioxide, methane, nitrous oxide, and fluorinated gases in the atmosphere. Together, they heat up the atmosphere by trapping energy. While CO2 has always been part of the atmospheric makeup, it has changed since the Industrial Revolution.
In the pre-industrial age, the CO2 response to temperature was that the temperature would go up and CO2 would go up. or if the temperature went down, CO2 would go down. And the reason for that is when the temperature went up, the whole biosphere revved up and emitted CO2, and we had more CO2 in the atmosphere. So we understand that process. The problem for the science community is in the post-industrial age, the CO2 rise is preceding the temperature rise. So two different things happened. One, pre-industrial, where temperature was driving the CO2, post-industrial, where the CO2 is driving temperature, which means a completely different physical, biological process is going on. And we don't understand what the consequence of that change is. It is a fundamental change to how the Earth works and how the Earth's radiation balance works. And so, since we don't understand it, we're very concerned because we don't see any restraining force on continued increase in temperature due to continued increase in CO2. And that's a problem.
Warmth tipped the scales again with the hottest October on record, but also the fourth hottest year to date for the globe, according to a fresh analysis by scientists at NOAA's National Center for Environmental Information. Generating long-term data sets is extremely important when studying climate. So, to maintain continuity, a new generation of Earth observation satellites are coming online. ESA have deployed Aeolus, METOP-3, Sentinel-C, and NASA have launched ICESat-2, the JSSC, and the follow-on GRACE missions. All of these satellites have one instrument in common that measures altitude.
A radar altimeter is a beautiful instrument because it measures almost everything we need on the planet. It measures the height of the sea, the height of the ice caps, but also we can use it to measure the heights of lakes and rivers, even derive river discharge.
METOP-C, the third in the METOP program, carries no fewer than 13 observational instruments. Some are identical to NOAA's suite of satellites.
We have 10 instruments on board METOP. It was a very large platform. And these instruments are also provided by different organizations. We have a set of instruments provided by NOAA NASA. We have instruments provided by CNES. We have instruments which are procured by ESA, and some other instruments which are procured by EUMETSAT directly.
So METOP-C is the last satellite of a cooperation program that we have with the NOAA in the United States as part of what we call the initial joint polar system. So in 1998, EUMETSAT and NOAA signed this cooperation agreement where three European satellites, so three METOP satellites, were corresponding to three US satellites. And for these satellites, we share instruments so that the users get information from both satellites, the same types of information. So we try to create synergies between US and Europe, more benefits to our user.
We didn't expect we'd be able to measure sea level to just a few millimeters every 10 days. And having such accurate measurements for 25 years let us monitor sea level rise and even perhaps detect an acceleration in the sea level record. And that was something that wasn't envisioned 25 years ago. But as the technology has gotten more and more accurate, we've been able to make more and more accurate measurements of sea level. And so we can be even more confident in our results. Combined with, we have other observing systems other than altimetry. We have a gravity mission called GRACE, where every month we weigh the ocean. And we have robots that float throughout the sea, about 3,000 to 4,000, that take the temperature of the ocean every few days. So when we add up the results we get from the gravity mission where we weigh and where the Argo floats where we take the temperature, we get almost exactly the same answer that we get from the radar altimeters to within a few millimeters. So we're very confident in our results that we're seeing 25 years of sea level rise of about 3 millimeters per year, which doesn't sound like a lot, but as we see it starting to increase year after year, we know that acceleration will be very devastating for coastal communities all over the world.
Aeolus, ESA's newest Earth Explorer satellite with which the agency will measure wind profiles from space with laser technology.
At the moment, we have a very poor understanding of how the wind is around the globe, and we need more knowledge about that. But that's the information you need to start. You need to have a picture of how is the weather now to be able to predict how the weather is in the future.
Aeolus is a relatively short mission to demonstrate the potential of the Doppler wind LiDAR in space. And once we can demonstrate that actually it's made a decent impact on the numerical weather prediction forecast, then hopefully we can have an operational follow-on mission, or maybe several satellites in tandem rather than just one satellite. It's not just wind information, actually. You need to also know temperature information, pressure, and humidity information. But the winds are a key component of that information that you need to know right now to work out the weather in the future.
Sentinel-3A was launched in 2016 and 3B in 2018. Both satellites primarily focus on our oceans. They measure the temperature, color, and height of the sea surface, as well as sea ice thickness. These measurements are needed to study changes in sea level, marine pollution, and biological productivity. Sentinel-3A has already yielded interesting results.
The Sentinel-3 mission is actually quite a versatile mission in the sense that it serves a large variety of different Copernicus services. So we're not just working with the Marine Environment Service, we're also working with the land, with the atmosphere, and with the climate service. There's a large variety of data that we can actually supply. The Marine Service is probably the most developed for the moment. It's already using data over the ocean, in particular the ocean color data, which tells us something about the marine ecosystem, about the health of the sea, and can basically also predict something like harmful algal blooms. Snow cover gives us an idea about the snow water extent. So basically that gives us an idea of when this melts, for example, where we go in terms of flood forecasting, runoff models, so for hydrological applications, but also for weather forecasting, for example.
Sentinel-3 mission is supposed to last until 2040 at least. So A and now B will be in space soon. The C and D model, which are replica of this one, are under manufacturing now and will be completed by the end of the decade. And they are expected to be launched in the 2023-24 timeframe to cover basically the Sentinel-3 mission until 2030.
That's why we want to have continuous measurements. So we have planned with the next series of JASON missions, JASON CS or Sentinel-6, that we'll have at least 10 more years of measurements because we need to keep monitoring the sea level as it accelerates.
With this long-range forecasting, the acceleration of global warming can be monitored and better predictive models developed.
Yes, that's why by having all three measurements, that helps us understand the cause, that we can see from GRACE a measure of which continents the water is coming from, that Greenland and Antarctica are melting, and some glaciers are also melting, and we can also see as the temperature of the globe increases, we can watch the water in the ocean actually expand for more and more heat.
Scientists on the ground continue to innovate ways to improve satellite data accuracy. Surfing for science may seem far-fetched, yet that is exactly how Dr. Bob Bruin of the Plymouth Marine Laboratory is pioneering a new technique in satellite oceanography. By equipping his surfboard with a device called a smart fin, Bob can measure sea surface temperature and motion of coastal waters with his smartphone. Later, Bob can use the smart fin data he has gathered to better interpret Sentinel-3 satellite data. The Sentinels are part of the Copernicus program. Using the three instruments on board, the satellites gather information on ocean color, water quality, changes in sea level, and, most important for Bob's research, sea surface temperature.
With over 40 years of thermal radiometry we have now from our satellite platforms, we can begin to get a really good understanding of how temperature is changing in the nearshore environment. And temperature is a critical component of our oceans. It controls the biology, through changes in growth rates and reproduction. It controls the physical environment together with salinity. It controls the density of the ocean, how coastal currents move, and it's also a fundamental component of marine chemistry. The reaction rates of many chemicals are temperature dependent. The gases that move from the atmosphere to the ocean are temperature dependent.
In situ data gathered by scientists like Bob is extremely important as it complements and helps to verify data provided by the Sentinel satellites. For example, the temperature of coastal waters is difficult to measure from space, though they have very high levels of marine biodiversity. So scientists find new and ingenious ways of increasing the number of in situ measurements in these waters. With the SmartFin, for instance, surfers and other water sport enthusiasts can gather data while enjoying their hobby. Meanwhile, NASA has dispatched 2 new satellite missions to observe the most critically changing regions, the poles. NASA and the German Research Center for Geosciences, GFZ, has launched GRACE-FO, continuing the revolutionary gravitary measurements of its predecessor, GRACE. ICET-2, with an advanced laser altimeter system, is continuing the work of its predecessor. This new technology will help study ice sheets, but also sea ice, glaciers, permafrost, and snow cover. Collectively known as the Cryosphere, these frozen zones help sustain stable conditions for life on Earth.
ICET-2 is NASA's latest technology to measure the elevation or the height of ice sheets, and by repeating those measurements through time, we can measure how ice sheets are changing. It'll also allow us to measure the height of sea ice, which is a way to understand the thickness of that sea ice. And so it's really a huge advance forward in both our precision of elevation change measurements as well as coverage. Each of those 6 beams gives us much more data than we've ever had before. ICET-2 is designed and built here at NASA's Goddard Space Flight Center, and it does take advantage of many of the latest advances in that technology. It's really an excellent tool for studying changes in ice sheets and in sea ice. For sea ice, it's really critical. It plays a first-order effect in weather patterns around the world. Sea ice in the Arctic Ocean regulates the exchange of heat and water vapor between the ocean and the atmosphere. And as sea ice gets thinner or thicker, it either allows more or less of that heat exchange to happen. For ice sheets, as that ice is lost back to the ocean, it directly goes into sea level rise, which of course impacts folks worldwide.
So NASA scientists crossed the Antarctic, taking altitude and radar depth measurements to help calibrate ICET-2's instruments.
One of the other experiments we were doing is leaving out what we call corner cube reflectors to get an assessment of the pointing of ICET-2. When we make an elevation measurement, how are we sure it's in the right place? So in this picture, you can see a bamboo pole with a little white cap on the end of it. And embedded in that cap, a little piece of glass about as big as your pinky nail, and calibrated to return green laser light from the satellite.
With the requisite observation tools in place, the next step is to interpret the data.
Ice sheets are actually really dynamic, and they flow under their own weight from the center of the ice sheet out to the perimeter of the continent. In the really cold regions and way high up on our ice sheets, we get a lot of snow accumulation, and over time, that accumulation can build up. If it stays cold enough and that snow persists, and then you get another year of snow and another year of snow, you can imagine the weight of the snow on top of itself forces some of the lower layers to compact. We call that the firn densification, the top layer of the ice sheet. When we talk about the health of our ice sheets, we talk about the mass balance of the ice sheet. Basically, that means coming in is in balance with all the terms of water or ice going out.
The health of the ice sheets depends on a balance of these terms of input and output. But the interaction of the atmosphere, ocean currents, and temperatures can force the ice sheets out of this equilibrium.
At a big scale, the winds in Antarctica are kind of spinning in a big clockwise direction around the continent. But you can imagine a big dome of ice has very little obstruction, like trees or mountains kind of steering the winds. Consequently, winds that sort of are gravity-driven and come down the continent can build up speed really quickly and, again, uninterrupted by any sort of disturbance. And we call those katabatic winds. And they have a major influence on what happens at the edge of the continent. Around Antarctica, there's a massive current that we call the Antarctic Circumpolar Current, and it flows clockwise around the continent. Close to the continent, we also have the Antarctic Coastal Current, stays really close to the coastline and flows counterclockwise around the continent. In addition to these continent-scale currents, we also have regional scale currents, such as gyres. Gyres are these parts of the oceans that are sort of isolated because of topography or ocean bottom topography. They're usually closed currents that often circulate. The gyres have a big role in sea ice formation and also in the currents that actually flow underneath our ice shelves. You can imagine that around the edge of the continent, near those ice shelves, warm water from the ocean can intrude into that cavity and contribute to basal melting, the melting from warm ocean waters of the bottoms of our ice shelves. Calving in Antarctica is a little bit sporadic and it's hard to actually model, but some of the contributing factors associated with calving include those strong katabatic winds pushing on the edge of the ice sheet, pushing on the edge of the ice shelf, and calving large icebergs. So we're measuring surface elevation, and we can take that vertical measurement, kind of integrate it over the whole ice sheet and get a volume change. And then the real science of ICET2 is taking that volume change and turning it into a mass change. And from that, we can determine how much ice is actually turning into water in our oceans and raising sea levels. So the Greenland ice sheet is thinning, and it's thinning variably, but mostly along the coastlines. It's thinning beyond our expectations. And all of that thinning is taking place upstream of where the ice sheet is grounded. Therefore, that is going right into the ocean and contributing to mean sea level rise.
Since we launched ERS-1 in 1992, we have been working on the radar altimeter time series, and we have derived a 25-year-long time series of sea level rise. Sea level rise is a major indicator of climate change because it integrates, for instance, the melt of Greenland and Antarctica. We have analyzed this series and we have analyzed the error, which is under control, and so the scientists are convinced that now we have clearly on average 8 centimeters of sea level rise, but we also have regional variation. For instance, in the tropics, it's 3 times that value. And what we have also analyzed with the recent data is that in the last 5 years, sea level has been accelerating. So it's not 3 millimeters per year or 3.2 millimeters per year. It's more like 5 millimeters per year. We have provided this data to people doing projections, to scientists, climate change scientists doing projections, and they have modeled the sea level in 2100, which is expected to be 2 meters higher than today.
This animation shows how different the globe will look by then and prompts us to consider where the food and fresh water will come from. Astronauts and cosmonauts, we've seen them train and study for years to enable these select people to work and live aboard the International Space Station. We have seen countless hours of their activities live on television and in the media. With this wealth of experience and insight behind them, what do they think when they return to Earth? Without exception, these spacefarers simply cannot wait to get back into space. Astronaut Paolo Nespoli is on his third space mission.
It's what I call becoming an extraterrestrial person. You know, it's losing your earthling things, and now you are really an extraterrestrial person because you don't think anymore about gravity, you don't think anymore about up or down, you think about what you need to do and position yourself so you can do it in the best way. You need to get used to working, to live first in space, being able to be very confident in the environment where you are. You need to be able to learn to translate extremely efficiently without banging into things. You need to be able to carry stuff. You need to be able to learn how to move around and do things, and how to sleep efficiently, how to work efficiently. And this takes like a month and a half. So after that time, you are fully ready to work, and that's why 6 months, because you have the capability then of performing at 100% of your capabilities, and then, you know, after 6 months, I think people are ready to go back to Earth and, you know, taste again the food, smell the air, see their friends, their family. For me, it was an exhilarating experience. I mean, I found this thing of trying new things. I find it really good. I felt I was like a little kid trying to do something, you know, try to get crazy and get inventive. And sometimes I thought, I should try something like that. And I said, that's not possible. It's never going to work. And then you try it, and you see that it opens up all sorts of other things that you never thought about it. And that it's a very good feeling. I mean, this feeling of discovery. The astronaut in space is one of the resources of the space station, and the control center want them to use as much as possible, so they have to make sure that they can work. In fact, we do work from 7:30 in the morning until 8:30 in the evening. That's the working day, and Houston and the other control center make sure that it's filled with activities. About 50% of that time is used for maintaining the station. We need to fix things, we need to move equipment, we need to change experiment, we need to load and unload spacecraft, we need to prepare for spacewalks. This is an important part. And then another 30 to 40% is actually scientific work. I am an engineer, an aerospace engineer, but I will do experiments that have to do with genetics, with medicine, with life science, with metallurgy. And we have a complex set of experiments spanning 360 degrees.
Which is a sealed environment. I'm going to open up.
It's a little bit going to school, yes. It's a little bit like the adrenaline that pumps in when you are in an exam, and you want to, from one side, you want to show off. You want to show all the things that you know. In the other side, you need to be careful, because some of these things can be very tricky, and it's easy to misunderstand something or getting too much involved in one thing and forget about the other one.
There are currently 16 active members of the ESA astronaut corps. Paolo is among the oldest. At 60, this is his third flight into space.
I feel really honored to be able to fly in space again. It's a very nice experience for me. I'm looking forward to use all of this investment that the agency have made in the past year to qualify me, all the personal investment that I made in get qualified and stay qualified, and use it again, go to space and be useful. I mean, I'm 60, but I'm going there, and I'm expected to perform as anybody else and carry out my task, and I'm looking forward to do what is needed and possibly a little bit more.
Other ESA astronauts who have experienced their first missions in space are already in training for their next. Alexander Gerst has spent 165 days in orbit with 6 hours of EVA experience. Even though he is well aware of the amount of work and effort that lies ahead, he's keen to get back into space.
It's a fantastic feeling to be back in training, of course. You can see the training facilities right behind me, and you can see why it's so interesting. I mean, this is like a full-on mock-up of the space station, so this is really the closest you can get on this planet to how the space station feels and looks like. And I've, of course, missed it a little bit after my last mission. I returned in 2014, that's 3 years ago, so it feels great to be back in that working mode.
He'll certainly be continuing some of the research he started in orbit back in 2014. On top of this, he'll be fulfilling a new role, that of ISS Commander, a job which requires a high level of responsibility for the station and its crew.
Of course, a new part to my training is that on my next mission I have the added responsibility of being the ISS commander, and to me that's a great honor. So I'm very humbled by the trust that people have in me to actually command this fantastic space station. But of course, it comes with a big responsibility also already in training. So that means I'm right now not only responsible for my own training, like in my last mission, I had to make sure that I'm trained and I can do everything that people need from me in orbit. Now I have a crew to take care of.
Another key element of the returned astronauts' life is to impart their considerable experience in order to help train the next rookie astronauts. Matthias Maurer, ESA's newest astronaut, has been training with astronauts Tim Peake and Luca Parmitano, both of whom boast extensive EVA experience.
It's actually a lot of fun because I can relate what I'm doing on the ground to what I did in orbit, and it gives me perspective to how it's going to be while I train. And as a matter of fact, our feedback to the instructors is very well received because we can improve the training that we receive just by getting our experience into the equation.
It's great to be back in Houston training again. I'll be in the neutral buoyancy laboratory very shortly with Matthias Maurer, the German astronaut, so my ESA colleague. Really looking forward to that as well, trying to sort of impart some of my knowledge from my spacewalk and to share my experience with Matthias. Here in Building 9, of course, it's great to be back, reminiscing about my time on the space station, but also learning about the new developments that are constantly changing on board the space station.
Don't tether to this D-ring on the bottom, that's only for the battery. The other thing too is that you can shove this all the way in here and then on this foot.
I have so many fantastic images and wonderful memories of my 6-month mission to space. If I was to have to choose one highlight, I would probably say the spacewalk was the highlight. Just going out of the hatch and seeing space, seeing Earth, and looking back at the space station from inside a spacesuit, that really was another order of magnitude over and above just the experience of going into space.
You put your toolbox down here, and your toolbox will stay because the water will keep it and the gravity will keep it. In space, you put your toolbox down, you look back, and it's gone, and it's up there, and it's all over the place. So, and all the tools inside your toolbox will all be floating around a lot more. So, the microgravity is really difficult in space.
I was at the NBL earlier this week, and just seeing the suit-up operations and seeing the suited guys going down for their spacewalk training, it really brings into perspective what the realities of a spacewalk are versus the NBL. And you know, there aren't that many. The NBL really is a fantastic place to train for a spacewalk. It's the best place that we can train on Earth.
Yes, and actually this is a good opportunity whenever you're heading out the airlock.
All European astronauts get training on how to operate in a spacesuit, in the American spacesuit. And so we need to learn how the spacesuit works, how it functions, and also how difficult it is to work inside such a suit. It's very limiting, and like a work that takes us 5 minutes here on the ground, in space it takes me half an hour. And afterwards my entire body aches, and it's hard work outside on the station.
And try to do hand over hand. And Matthias, you don't have to ingress the APFR. We could have drivers.
pause for a second to figure out which... I hope that I get the chance to do a spacewalk, because all my colleagues told me a spacewalk, it's like the best experience of your space flight. Leaving the station, seeing the station from the outside and having a very clear picture of the Earth below you without being limited by a window, just looking through your visor. That is, the perfect image, and I'm really looking forward to it. I'm happy that I'm out of the water and that I actually can move my arms again, how my body is designed to move the arms, because the suit constrains a lot of my arm movement.
We thought it'd be a great idea. It kind of serves its purpose, but we found better techniques like safety tether paths.
When you're in there in that position and you've got your gravity here, you've got your gravity and everything, just even to see the unlocked
I couldn't see it.
It's good to just have one wire tie dedicated to a bunny ear. And of course you can pop this down and pop that up. Mine is this direction here. I like the joint to be on top because you'll find in the pool you need this to maintain your rigidity.
This right now is in mortar, so in order to do the cal test, you need to either put it in retroclockwise or counterclockwise. There you go. That's a little different. Now you get your LED test, and now you know all your LEDs are working. Don't tether to this D-ring on the bottom. That's only for the battery. The other thing too is that you can shove this all the way in here, and then put on this foot. It's not new to you. You know that you're going to go ahead and stick your boot into the toe loop, put your heel down,
and foot in, and then I lean backwards.
When we were in orbit, we had 3 spacecraft come up. We had Cygnus, we had HTV, and ATV. ATV was all the way aft, and you have to cross all of the Russian segment in order to transfer cargo to the other side. And you would really need some coordination with our Russian colleagues, because if they're working doing sport, then you're floating in the middle of all their activities.
So the station does become a very busy place.
Even in shape, there are modules that are in a different position than compared to when I was up there, and the procedures have changed compared to when I was up there. Specifically the emergency procedures, and all of the payloads are different. So all the training has to be done completely from zero.
The seasoned astronauts still get a kick out of looking to the future, especially when it comes to new equipment and spacecraft like the Orion capsule.
Visiting the Orion capsule today was really exciting, and it's the next stage in our space exploration. Europe is very much a firm partner in there. We're providing the service module for the first exploration missions, which is really exciting. Going back to the moon with a vision of using that same vehicle for some form of Mars transportation vehicle.
Currently, we are flying to the ISS, but the ISS program will soon become to an end, or it will become a commercial space station. On the other hand, we are also looking to fly much deeper into space. The ISS flies at 400 kilometers altitude, and with the Orion we can actually go into deep space, for example to the moon, which is 400,000 kilometers, so 1,000 times further away than the ISS. And actually this opens a new perspective into exploration. We will go to the moon, and after the moon we will go to Mars. And there are lots of adventures, lots of science that we can do in deep space.
Experience isn't the only thing astronauts bring back from space. Their biological specimens help evolve the gastronomical sciences.
Here we are opening the samples we received from Thomas, coming directly from the ISS. There are different samples of urine collected during 10 days of tests.
Providing enough energy for the astronauts is a critical aspect of payload planning, particularly for long-duration flights.
The centre will provide us with an inventory of all the food taken by Thomas up there for all the time of the exercises he made during the 10 days of our tests. Here, for example, we can see on this table the energy consumption of Thomas every day, how much he has spent.
You can't order pizza to go in orbit, so the decisions about what to take with them can be critical for astronauts.
Food is something that's really underestimated down here in the ground. Like, people go like, oh yeah, I'm going to fly to space, I don't care what food I take. It's not bad. Well, you start caring about that 1 month into the mission, and then if you made the wrong decisions, it's a hard remaining 5 months. This is mainly to trigger my memory for the food that I already had, and now I can make the choices based on how I remember them. And then there's a few new ones in between. For them, I have to sort of guess. There's still debate if the taste actually changes the actual taste buds, if people perceive taste differently. My personal opinion is we don't. I think it's the same, but the cravings change, and that is really hard to predict. Right now, I might not care so much for broccoli and cauliflower, but up there, I really liked it. Because it's pretty protein loaded. What we have a lot of meats. And then I tried to add anything that reminds me of something green, let's put it that way. I mean, those beans, they don't resemble beans a lot, but they actually taste really nice. Oh, we didn't have blueberries last time, right? We had raisins. That stuff is awesome. Last time I got a few Russian bonus containers. They also have very, very good food. Their food is more succulent, like they have more grease in there, also more spices, also more salt, which is not so good for the bones. So I tried not to eat so much of it. The American food or the European food is more healthy, I would say. But once in a while, it's really satisfying to just open a can of this really succulent, savory Russian food, and I absolutely enjoyed it. It's really good. On my last expedition, we tried to have the meals all together. The US crew, European crew together, we always had meals together when we could. And then on the weekends we would gather, like the 6 of us. Either the Russians would invite us to their segment or we would invite them. And then we have the big table and everybody brings something together and it's kind of this medley. That's important. Those are the relaxation moments. You can take a time, you put music on and you chat about how your week went. And it's the last thing that I have for today. After a successful tasting of 48 items.
With experience comes cooperation. ESA is now conducting astronaut training activities in China. Samantha Cristoforetti and Ruki Matthias were each teamed with 2 taikonauts, who between them have considerable spaceflight experience.
We are basically practicing what would happen if there was an off-nominal landing. We wouldn't land on the ground, but we would actually land in the water, and we would have to survive independently for some time and using the rescue boats and the rescue equipments and exiting, of course, the re-entry capsule autonomously.
After donning insulation and buoyancy suits, they practiced rescue procedures with both a ship and a helicopter from a mock-up Shenzhou capsule. Space missions can be unpredictable, and training exercises such as these ensure that astronauts are prepared for every eventuality.
The training experience so far is great. The Chinese are really well prepared. It's a high-level equipment. We get helicopter airlifting. We have a huge sea survival rescue ship, which is usually employed on the high seas. So very good equipment and a very good experience so far.
Accompanying Samantha and Matthias in China were an ESA flight surgeon and a training specialist who gained insights into the different cultural nuances and approaches.
During this training, I have had the opportunity to work very closely with our Chinese medical colleagues, and I'm very, very impressed about how they have combined their traditional Chinese medicine, which has thousands of years of history, with the most advanced medical knowledge that we can find now in the world.
Training here is very, very well organized. So we have different ways of approaching training, which is inherited from the ISS program, but actually they are not that far away. So it means that we find common words and common understanding in the way they also organize this training. So for us, it's a very good sign for further cooperation with the Chinese.
This training exercise wasn't the first collaboration between the two space agencies. In July 2016, Chinese astronaut Ye Guangfu joined ESA's caving course in Sardinia to experience an extreme environment as part of a multicultural crew. Both activities stem from the 2015 agreement to boost collaboration between ESA and the China Manned Space Agency, with the ultimate goal of flying European astronauts on board the Chinese space station from 2022.
This joint training we're doing here is a first step in a cooperation that we all hope will lead one day in the early 2020s to a European astronaut flying with the taikonauts to the future Chinese space station. And so, of course, I would be thrilled if I had that opportunity.
Organized by the Astronaut Center of China in cooperation with the Ministry of Transport's Beihai Rescue Bureau, this training session has been an important step towards long-term collaboration. Space flight opens up new horizons, not just for astronauts, but for nations as well.
Yeah, so as you know, my last mission was called the Blue Dot. We focused on the view back, the perspective back from space onto our little planet Earth as it flies through the black universe. Now, on the new mission, we decided to take a step further, to even view with a bigger perspective, to acknowledge that it's not only about our little blue planet Earth, but that there's much more out there in the universe. And as the early explorers who sailed, beyond the horizon, towards the horizon, and even further, we named our new mission the Horizons Mission.
Set the controls for the heart of the sun. It's a dramatic statement familiar from movies and music, but now a new mission really is ready to plunge into the atmosphere of a star. Not just any star, our star, the sun. 60 years in the making, the Parker Solar Probe is primed to reveal the true nature of the heart of our solar system and the source of the solar winds. Weighing just 685 kilograms, the solar probe was launched aboard a ULA Delta IV heavy rocket. Its thrust of 9,700 kilonewtons may seem like overkill, but the Parker probe has to travel faster than anything before. As a matter of fact, it will be the fastest man-made object ever launched.
Parker's solar probe really is a historic mission. It was first dreamed of in 1958, and it's remained the highest priority mission throughout that period. The reason it hasn't flown is just because it's taken a while for technology to catch up with the dreams that we had for this amazing mission.
Destined for the sun, our star, this probe is the realization of a dream that has been evolving over decades through the talents of hundreds of dedicated people.
After working on this for 10 years, it is really a pleasure to see it kind of actually coming to fruition. To be one small part of this huge engineering team that is making science dreams come true is just amazing. I can't wait to rewrite textbooks and change the way we look at the sun forever. I'm really excited to pass this off to the mission operations team and see all the science data that comes down and just get to enjoy all that Solar Probe brings us.
This is a 60-year journey that people have gone on to make Parker Solar Probe a reality. And to be there at the finish line, that is definitely the coolest thing about my job.
Several questions arise. How did this project get started? Who was behind it? And why is it called the Parker Solar Probe? It's because of this man.
The Parker Solar Probe is the first mission ever to be named after a living person, our own University of Chicago astrophysicist Eugene Parker.
Born 1927 in Houghton, Michigan, Gene Parker gained his PhD from Caltech in 1951. By 1958, he had developed his theory on the supersonic solar winds and predicted the shape of the solar magnetic field in the outer solar system, which now bears his name, the Parker Spiral.
So Gene Parker had graduated in physics and had a hard time actually getting a job. So he was first doing some researching at University of Utah when he was then invited to come to Chicago. He was not sure he was going to make it in the field. When he wrote his paper, it didn't help that the referees were not in agreement with him and didn't really want to publish his work. So he had lots of challenges early on, but he was right. And this is one of the things that first helped him, be the person that we all recognize as this amazing role model to all physicists, but also the power of science being right or wrong due to experiments. So what vindicated him was not just having Chandrasekhar, for example, helped him publish his article, but what really made him who he is in the history of science is the fact that the measurements showed him right.
Eugene Parker has received many accolades over his career, including the National Medal of Science for Physical Science and the title of S. Chandrasekhar Distinguished Service Professor Emeritus at the University of Chicago.
So in 1958, Gene Parker realized that the sun has a magnetic field and it will have a structure around the solar system that will be populated by what we call plasma. So these are hot particles that are flying from the sun all the way to the edge of the solar system. This is what he called the solar wind. So the solar wind is a structure generated by the sun, which basically envelops the whole of our solar system all the way to the edge. And it has been studied all the way to the edge of the solar system with, for example, the Voyager probes, which are now crossing into what's outside of the solar system, which is the furthest that man has ever been, or any man-made machines have ever reached across the solar system.
I laugh about this because I remember how upset some people were. They insisted I made a mathematical error, and I would reply, well, here you are. Here's 5 lines of algebra. You say I made a mistake. Show me. And it's amazing the number of people that just couldn't let go of the old ideas. They've been working on the spacecraft for several years, and one day the phone rang, and it was a guy that I know said, we're talking about putting your name on the Solar Probe, Plus it was called. And did I object? And I sort of said, no, I feel rather flattered. So he said, okay, that's what we'll do.
While the success of this mission bearing his name will not be known for many years to come, all the effort is sure to be worthwhile. The advances in engineering required to make this mission successful have been far-reaching and at times ingenious. That's because the speeds required to reach the Sun are mind-boggling in themselves.
The solar probe will be reaching the closest ever to the Sun and moving the fastest and reaching the hottest regions of the solar system. It's so fast that it could go from Chicago to Beijing in less than 1 minute.
There are many enabling technologies. The solar arrays were very important. The autonomy was very important. One of the ones that was obviously also critical was the heat shield, and developing the technology to actually protect the probe at the Sun.
The Parker Solar Probe is a technological marvel. The thermal protection system, the heat shield, will be glowing cherry red. The front surface of that will be 2,500 degrees Fahrenheit, while the spacecraft remains 85 degrees, roughly a warm day in Florida. The material sciences just didn't exist in the 60s and 70s, and so the carbon, which came out of frankly the military, looking for lightweight, stiff, strong structures, were the precursors to your tennis rackets and golf clubs, which are now the precursor to the carbon-carbon technologies that we have on Parker Solar Probe.
Temperatures so close to a star can reach a phenomenal range. Serious sun screening is required.
And a sandwich panel is a lot like a honeycomb panel you find in a traditional spacecraft or on airplanes. You have 2 outer face sheets, and then you have a core. In this case, the 2 outer face sheets are carbon-carbon composite, which is a lot like the graphite epoxy you might find in your golf clubs. It's just been superheated. And then the inside is a carbon foam. So the Parker Solar Probe heat shield has a white coating that's on the sun-facing surface of this giant frisbee that's protecting the rest of the spacecraft. And that white coating was specially designed here at the lab in collaboration with RED and the Space Department, as well as the Whiting School at Johns Hopkins proper, to actually work at the Sun. This was specifically designed for Solar Probe. And the concept is basically you'd rather be in a white car on a hot day than a black car on a hot day. It's just that it just knocks down the heat that much more. And so it's helping us stay cool at the Sun. That titanium truss was also specially designed for Solar Probe. It's actually a really neat piece. It's a welded titanium truss that's about 4 feet tall, but it only weighs about 50 pounds. And the key there is we're trying to minimize the conduction between the heat shield and the spacecraft. So you want to have as little stuff there as possible.
The hottest environments in the solar system will be probed by this mission, and it's instruments that will be measuring all the different properties of the solar corona are protected by a shield, a state-of-the-art shield developed by NASA, which would make Captain America very envious. This shield keeps the instruments behind from being cooked every time the probe gets really close to the Sun. So the shield made of reinforced carbon is really something that is very recent technology, and only now we can actually get that close to the Sun and really verify some of the predictions that Gene Parker has made over his whole lifetime of trying to understand the solar wind.
Earlier iterations of this spacecraft design were predicated on a nuclear power supply. That idea was dropped in favor of solar panels, which brought their own design difficulties so close to the Sun.
Parker Solar Probe needs electrical energy to operate. Like any other satellite, or most other satellites, the spacecraft has solar arrays. But unlike other satellites, we have to generate electricity very close to the Sun. For every watt of electrical energy we generate, we have to dissipate 13 watts of thermal energy. To do that, we need a cooling system, and we have a cooling system that's much like you'd find in your car. There are 2 water pumps in the system that pump water through the solar arrays and up into radiators. Those radiators radiate the energy to deep space, which is very cold, as opposed to like a car where it would be radiated to air.
When we're at closest approach, the front surface of the heat shield will be at about 2,500 degrees Fahrenheit. The back surface of the heat shield will be about 600 degrees Fahrenheit. But then the spacecraft bus is basically sitting at 85 degrees Fahrenheit. So the shield is actually really keeping everything very cool, and that's most of the stuff is on the heat on the bus.
If you look at the science data, there's a big gap, and that gap is where Solar Probe is going. We're going to fill that gap of scientific knowledge. So it's true exploration. I mean, in that, and we're not following somebody. We're be the first spacecraft, first people to go there. So what will be interesting is not the answers to the science questions. What will be interesting is the new questions that Solar Probe forces us to ask. Because one thing we're pretty sure of is that probably have it somewhat wrong. Solar Probe will teach us what's right. And that'll generate many, many more questions and many more missions to come.
NASA's Parker Solar Probe will soon fly closer to the Sun than any spacecraft before it, some 4 million miles from the visible surface. But getting that close to the Sun requires some fancy orbital mechanics and a dash of brute force. Why is it so hard to get to the Sun?
Another reason Parker Solar Probe wasn't launched in the last 60 years is that getting so close to the Sun is hard. It takes a huge amount of energy to get to where we want to go. When a satellite lifts off the Earth, it carries the Earth's velocity around the solar system. So the Earth is moving at about 30 kilometers per second around the solar system.
Of all the space missions I've worked on, Parker Solar Probe is the most challenging and complex mission to design and to fly. The launch energy required to reach the Sun is 55 times of required to get to the Mars and 2 times to Pluto.
Traveling so close to a star can also affect communications with Earth. In such a dangerous environment, engineers had to design software with serious smarts.
So Parker Solar Probe uses a sophisticated rule-based autonomy system to protect itself. For long periods of time, the spacecraft can't communicate to the Earth, and it needs to take care of itself. So the engineers during the development phase spent a lot of time thinking about what faults could affect Parker Solar Probe and came up with solutions for those faults. Those solutions are encoded in this rule-based autonomy system so that even if there's a fault on orbit, which of course we hope there isn't, the system can take care of itself. One of the most common questions I get are, what happens if the spacecraft gets hit by a solar flare or gets hit by a coronal mass ejection? Will it be destroyed? That's a very common question. And what I tell people is the science community will be elated if we were to get hit by a solar flare or a coronal mass ejection. They're very dramatic events when you look at them in a telescope or during an eclipse. But in the reality, they're very ethereal. The density of the particles isn't so high from the point where it could actually cause damage to the spacecraft. But the instruments aboard the spacecraft, the electromagnetic field instruments, the high-energy particle instruments, the plasma instruments, and the visible white light sensors will see this event. And how dramatic would that be to see a solar flare coming at you and fly right through it?
The sensor suite on board the Parker Solar Probe is indeed impressive. Each was designed to withstand the harsh radiation and temperatures to measure the particles, electric and magnetic fields of the solar wind. There is also an imaging instrument on the spacecraft called WISPER.
The WISPER instrument is the only imaging instrument on the Parker Solar Probe, and it is looking in the direction that the spacecraft is traveling. And what it sees is light scattered by the dust that's in orbit about the Sun. But then, once we remove that, what we see is the light scattered by the electrons in the corona, in the solar wind. These measurements that we're making from the WISPER instrument have been made before by other instruments from 1AU, from the distance of the Earth, about 100 million miles from the Sun. By getting closer, we're increasing then the ability to see what's really close to the Sun. The fact that you're close means that you don't have all this material that's in between you and the object that you're really interested in. And that contributes to background noise. And so you're looking at something that's much more pristine. You're looking at just that object all by itself.
We have 3 sensors that measure magnetic fields that are mounted on a boom behind the spacecraft in the shadow shield. And then we have 5 sensors that measure plasma voltage. These are electric field sensors. They extend into full sunlight and they get very hot. There are 2 ways to measure electric fields in space. One is using a technique that's called a double probe. Then there's another technique which is measuring plasma waves or radio waves. And Fields for the first time brings these 2 techniques together. I think the very first data that we get will be revolutionary. At first blush, it'll just be a bunch of numbers as a function of time. But the science team, will take those numbers and make visualizations in the form of spectrograms, and eventually those data will be related to models, and so we'll be able to compare directly the 3D visual models of the coronal magnetic field. 2 of the key measurements to understanding coronal heating are the measurement of the magnetic field and the electric field, and together they give us what's called the Poynting flux, which is the energy flux of the corona. And to make those measurements, we have to actually go into that plasma and put sensors in the plasma to measure magnetic fields and electric fields directly, and that's what Fields will do. These measurements have never been made in the environment close to the sun. We've made measurements similar to this in the Earth's magnetosphere, Earth's ionosphere, but putting a package like this into the solar corona has just never been done. The closest anyone's ever been to the sun, and based on what we've seen so far from spacecraft not quite as close, it's going to be striking and I think revolutionary.
The other science packages aboard Parker include SWEEP and ISIS, designed to study the particles emitted in the solar wind.
ISIS, the Integrated Science Investigation of the Sun, is an experiment which looks at energetic particles over a broad range of energies, from tens of thousands of electron volts up to about 100 million electron volts. The ISIS instrument is based on solid-state detectors. Those are detectors that when a particle passes through them, energy is deposited, and you can measure that energy, and you can measure that the particle has actually passed through. So there's the solar wind, which is this continuous flow of lower energy particles. And then there are much more sporadic and episodic events like solar flares that spew out great numbers of these much more energetic particles. In our higher energy instrument, we have a whole set of layers of these detectors. And when a particle passes through those layers, it leaves energy in each and every one of those detectors. Those detectors are also segmented in pieces like a pie. And so when a particle comes through from a particular direction, you can tell both the direction the particle came through at, and you can tell the energy and species of that particle.
The SWEEP investigation consists of 3 separate instruments and a central electronics box. Most of the instruments within SWEEP sit on either side of the spacecraft, stare out over the entire sky, and make maps of all the different particles and what energies they're moving at, what types of particles they are. The purpose of SWEEP is to measure the bulk of the solar wind and the solar atmosphere. One of the biggest questions we want to resolve with Solar Probe is how the corona and the solar wind are heated. In order to do that, we need to see if there are waves that are coming from the sun and depositing energy within the solar atmosphere and in the solar wind. So we have a series of sensors across the spacecraft that will collect individual particles, electrons, fully ionized hydrogen and helium, which we call protons and alphas, and other minor ions, and make maps of the number of particles as a function of their speed and energy and type. We take those maps on the ground and we can interpret them to figure out the temperature, the density, the pressure of the solar wind and the solar atmosphere.
Learning the secrets of our star, the Sun, will help us understand the nature of the solar system and its all-embracing influence on our world. But the Parker Solar Probe is not the only mission destined for that star. The European Space Agency is also in the game. In collaboration with NASA, the Solar Orbiter is set to launch very soon and will be joining Parker in its quest for knowledge. The orbiter will fly an elliptical orbit within the orbit of Venus, but on a much greater inclination off the ecliptic, giving it access to the poles of the Sun. Unlike the Parker probe, the orbiter's main observation instruments will peer through the solar shield at a safe distance, then reconfigure when making a closer approach. Together, they will reveal the secrets of our closest star, the Sun. The tenuous envelope of gas surrounding our planet is an unbelievably complex machine that protects us from the vacuum of space, shelters us from harmful radiation, and allows us and the biosphere to breathe. It is our atmosphere, and we need to learn much more about it so we can take better care of it. Soon, the European Space Agency ESA will launch its new Earth observation satellite called Aeolus. Using cutting-edge laser technology, Aeolus will provide near real-time observations of wind profiles across the globe. These will improve the accuracy of numerical weather prediction and climate modeling, and advance our understanding of global atmospheric dynamics.
Aeolus is one of the Earth explorers that is going to look at the Earth, trying to understand the wind profiles globally. And that's a first, it doesn't exist yet. The whole idea was that we only have wind measurements on very different small spots on the Earth, and we didn't have it globally. So the mission scientists had been asking for this because it's a gap in our measurement system.
The mission aims to expand our knowledge of our atmosphere and weather systems. Aeolus will achieve this by providing global observations of wind profiles from space, providing data which has never been available before.
It's unknown ground. It's what we call uncharted territory. So we are the first agency trying to get a satellite in orbit that looks at the Earth with a laser and trying to understand the wind profile, so the direction, the height, and the wind speed. And therefore improving the weather forecast. Because nowadays we only have at single points balloons that measure the wind, or airplanes that give us some data, or at fixed points, at discrete points. This will look down to the Earth in a polar orbit, will dump every 90 minutes the data to Svalbard. That will be distributed to all the European meteorological institutes. And then when you're sitting at home on your couch, you watch the television and you see a weather forecast that is much better than we have it today.
Aeolus will fly in a sun-synchronized polar orbit 320 kilometers above Earth's surface. Its data will be sent to ESA's Svalbard ground station, located in the archipelago halfway between Norway and the North Pole, every 90 minutes. The satellite's main instrument is Aladdin.
Yes, the way the Aladdin instrument works is to eject an ultraviolet beam down through the atmosphere, and then particles of moisture in the atmosphere at various levels are in motion because of the wind, and the system measures the backscatter from those particles using the Doppler effect and can detect the wind speed at the various altitudes. And that's the way the system operates.
The development of Aeolus has been a long and difficult process, with new and cutting-edge technologies designed, developed and tested on the ground.
It has been a very difficult challenge, let's say. It's a long line because it exists already for 16 years, the program. And when we first had the part of the instrument, when we switched it on, it worked. Then we put it in vacuum and it stopped working. And no one had realized that we needed oxygen inside the satellite to keep the laser active. So it was quite a challenge, so we had to develop a whole new set of techniques. It's maybe a bit too detailed to go in all the details, but as a lot of technology has been developed, put in this nice little satellite which is behind me.
Aeolus is another ESA Earth Explorer mission aimed at pioneering new technology while providing useful data about our ecosystem. It showcases the technological expertise of the European space industry and ESA's objective of monitoring and understanding the planet we all live on.
The main challenge for us has been within the development of the Aladdin instrument. There's a very high-powered ultraviolet laser system in there that is an inherent part of the instrument. And the technology behind that laser system, the development of a stable laser, high-powered laser beam, and the optics that then focus and divert that beam through the system is very critical, and that's been a very key part of the development. After many years and much hard work across the European industry, we've overcome those problems. We've got some new development through coating technology on the optical surfaces to protect them. And we've now got a stable system that's been fully tested on the ground, and we're ready to go.
The tracking of air pollution is also part of the European Union's Earth observation program, Copernicus. One of the satellites that gave scientists massive amounts of data on atmospheric pollution was ENVISAT. This satellite used several spectrometers to detect ozone and trace gases in our atmosphere. The latest satellite, the Sentinel-5 precursor mission, was recently launched and builds on that legacy of ENVISAT.
So we started this precursor mission because the scientists wanted continuity of data. At the moment, we only have one spacecraft doing that job for us, which is OMI, and OMI is coming towards the end of its lifetime. The next missions that will do this job is Sentinel-4 on metopside generation, which will only be launched in early 20s. In the meantime, to ensure a continuity of data, we need Sentinel-5 precursor. It will be the only such mission doing this job until then.
Sentinel-5B is a precursor to the Sentinel-5 mission, which should be launched around 2021. But it's not only a precursor, it's also a gap filler, because it's filling the gap based on the data that we have coming from GOMES, Kirmaki and OMI measurements towards this future Sentinel-4 and Sentinel-5 missions.
Sentinel-5P is the first atmospheric chemistry mission within Copernicus. Its main instrument is a state-of-the-art spectrometer called TROPOMI, which will be used to detect trace gases in our atmosphere. The Sentinel-5P satellite is a timely replacement for the ERS and ENVISAT after it stopped working. There was an urgent need to fill the gap in observing air quality and air pollution. Furthermore, according to the World Health Organization, air pollution is responsible for over 3.7 million premature deaths worldwide every year. But the health costs are even greater, as many people suffer from non-lethal afflictions either caused or aggravated by breathing polluted air. Another major health concern on which Sentinel-5P is gathering data is the ozone in our atmosphere. When that ozone is depleted, ultraviolet light from the sun is no longer filtered. Increased exposure to UV light can cause skin cancer, immune system damage, and other ailments in humans.
The tropomi data will be used operationally, so it will be used to improve the air quality forecasts. And air quality forecasts are of course important for people who are vulnerable to pollution, but also for the general public in case of big smog events. What we can do with the tropomi data is we can look at the emissions of pollutants. And when you see them changing over time, that is very important because we can see if certain policy measures have the right impact or where we see still increases and still have to do more to reduce the polluting emissions.
A decline in air quality, such as smog, poses massive risks for people's health. And one of the main contributors to climate change is the pollution of our atmosphere by greenhouse gases such as CO2 and methane. This is why measurements on air pollution need to be undertaken everywhere, like here, for instance, with a mobile measurement station at the University of Bremen. It detects smog and industrial emissions. These local measurements supplement and validate the global observations from satellites, which in turn are needed for scientists to study the air we breathe and the planet we live on.
Well, the satellites are a key information base and knowledge base for the study of atmospheric physics, chemistry, and meteorology. It's essential data because we need to know not just what's coming out at a given place, but we need to know where it's going, where it's depositing at the surface, how it's being transformed. Is it going to be taken up by clouds and rained out? If so, where? And this whole transport and transformation process is a complex business. In general, we have this problem of unambiguously identifying anthropogenic impact from natural phenomena or natural behavior in this complex system and how we're modifying it. So this is the challenge for the science, which is a necessary prerequisite to enable good legislation and ultimately sustainable development. So in this context, measurements from space are essential because they provide us with the global picture or from the local to the global scale.
The Sentinel-5P mission will have quite some improvements as compared to previous missions. For example, if you look at the spatial resolution, we will break a record, namely we will look at city scale because the nadir pixel size will be as low as 3.5 kilometers times 7 kilometers. So we can then investigate small-scale features over big cities and city agglomerates, for example.
The mission will monitor the atmosphere using the tropomi spectrometer to monitor various trace gases in our atmosphere and reduce data gaps between ENVISAT and Sentinel-5. By combining satellite data with the local measurements on the ground, scientists can properly monitor air pollution and how it impacts us and our planet.
We have lots to understand to assess the impact. Ultimately, more pollution is bad for health, bad for people, and the estimates are somewhere between 3 and 7 million people a year die prematurely from air pollution. This is a large number of people.
At the forefront of Earth observation, the European Space Agency helps us to understand climate change and pollution by giving scientists and policymakers the data that can drive legislation.
These atmospheric measurements are extremely important for mankind. First of all, to see how our planet changes in terms of climate, but also to see how air quality changes in different places and over time. We have highly polluted areas, which are, of course, transporting pollution from one place to the other. So these fluxes of pollution or gases is very important to monitor. But also, if you take Europe, for example, Europe has introduced very strong legislation and regulations in order to reduce greenhouse gas emissions. And this has also to be verified, and these satellites are a very good measure or very good way of making sure that these reductions are taking place at a large scale.
In the early 2020s, the space component of the Copernicus atmospheric services will be extended through the addition of Sentinel-4 and 5 missions. Sentinel-4 will be a geostationary mission, whereas Sentinel-5 will be a low polar orbiting mission like Sentinel-5P. Atmospheric services are part of the Copernicus portfolio, which comprises 6 main themes: marine, land, emergency, security, climate, and atmosphere, giving a complete overview of our planet's health and its evolutions.
Can have a lot of practical applications using the data from the Sentinel-5P mission. One idea would be perhaps if we look at the harmful UV radiation, you could set up UV radiation services so that people on the street, so to speak, in the sun like today, could inform themselves how harmful it is to receive this short-wave ultraviolet radiation.
The Sentinel-5 precursor data will be combined with models and other data to develop targeted services, and they will be available as apps, social media information, or web services, so that a lot of people can choose their way they want to be informed about the environment.
Atmospheric measurements are important because especially these measurements that are done by Sentinel-5 precursor, like tropospheric ozone, information about nitrogen dioxide, sulfur dioxide, also information about aerosols, particulate matter, they have impact on the health of people. They can impact the people who have problems with their hearts or with their lungs. And as it has been shown, there are more than 400,000 premature deaths in the European commissioning based on exposure to air pollution.
Air quality in Europe in particular, but also in the US and in Japan, got much better over the last years. That's a really big improvement. And at the same time, air quality in the developing countries, in particular in Asia, has gotten worse because they use much more energy nowadays, and that's a big source of air pollution. Also, if they are using more cars, that will pollute the air more. So it's different, depends on where you live. In some places air quality gets better, in other places air quality gets worse. I should add that in the last 3 years, air quality in China has improved because they are very ambitious about that and have very strict rules. So they are trying to follow the European or United States path in improving air quality with better technology.
Observation from space is just one of several methods of measuring atmospheric pollution. Satellites provide the data, although they need to be calibrated with measurements on the ground.
So we are offering a comprehensive analysis, integrating data at different scales. So we are using observations, we are combined with modeling, with satellite data, and all this information is complementing each other. This is the good thing of this kind of analysis. Satellites have the advantage of providing a global picture. Trends, you can study trends very well, how the main flows are taking place. But satellite data, they don't have the resolution to get in detail in the individual processes. So here, with our in situ measurements, we are getting in one particular point, and we get deeply in the detail.
the satellite gives these beautiful maps, but you can only use them really if you have a validation measurement to compare to, and this needs to be a very good measurement, and this needs to be taken on the ground. That's very important for us because we need to be very confident of the satellite data. And once you have launched the satellite, it's out of your hands and you cannot bring it to the lab and double check and test it. It's there and you need to trust the data. And the only way to get this confidence in the data is by comparison to other measurements.
Other forms of atmospheric pollution, such as the exhausting of carbon dioxide, methane and ozone, contribute greatly to climate change.
Well, I think basically it's often the case that our models, which are extremely complex and good tools, often don't necessarily have the right physics or chemistry in them to be able to predict what's going on in the future. So a lot of the time in atmospheric science we've been making discoveries. Back in the late 19th century, early 20th century, the discovery of the stratosphere was a complete surprise at the time, or fairly surprising. The fact that temperature increases above the tropopause. This was a surprising discovery, and really that's been typical. We didn't expect summer smog. We don't understand why in Paris there was a really big smog a couple of years ago in spite of improvements of legislation. This winter we had in London a smog which is maybe being attributed to excessive wood burning recently. So there's a lot of things although we're getting over the last 25 years much better information, but the satellites in particular tell us ultimately, or could tell us ultimately, what the source strengths are and enable us to follow the information and thereby, together with models, give really good prediction for people about the air quality that they're receiving.
The Copernicus program is very important for Europe and for the world. First of all, the Copernicus program is providing free data to everyone at any place in the world. So many users, not only in Europe, but also in America, in Asia, are using our data in a very large scale and very significantly. So therefore, Copernicus is really monitoring the health of our planet from all dimensions: the atmosphere, the oceans, the land surface, the ice caps, and this whole system of the Earth composed of these components is monitored constantly with Copernicus. And therefore it is really important to see what is the state of our planet and how it will evolve in the future.
Well, the data can be used for different applications. So for example, for the air quality forecasts, it's also used by KNMI, for example, for the UV forecasts. And we also use it to warn the aviation for volcanic ash plumes. On top of that, the data will also be used by scientists around the world to study the atmosphere and to study how man is changing the atmosphere over time.
It won't be long now before you too can enjoy a view like this. Economy or business class? There will be a variety of choices of carrier and cabin. The view will be spectacular. This is the traditional way to orbit, a Russian Soyuz launched from Kazakhstan. NASA has to pay in the area of $70 million per seat return trip, and prices are about to go up. Only the Chinese have an alternative launch system. Very shortly, there will be 2 carriers taking tourists into space on suborbital flights. Blue Origin will probably launch first with their capsule and reusable launcher. Next will be Virgin Galactic and their suborbital space plane, launched from beneath a carrier aircraft and landing like one too, although to what altitude is still not known. Then you have America's return to space with its 2 commercial partners. Boeing have their CST Starliner, the first launch-capable capsule already off the assembly line. Looking every bit like an Apollo spacecraft, it will be able to ferry crew to and from the ISS. An unmanned test launch to the space station is imminent, and the crew has been picked to undertake the first few missions. Their standout competitors are SpaceX and their manned Dragon capsule, performing the same vital service. They're hedging their bets in the tourist sector as well, with their BFR concept naming their first paying customer.
Thank you, Hiro. Thank you, everyone. Wow. I am from Japan. My name is Yusaku Maezawa. You can call me MZ, please.
After the success of the Falcon Heavy maiden launch, SpaceX is ramping up design and construction of its even larger rocket ship to Mars. However, the 2 other commercial entities aren't resting on their launchers either. Jeff Bezos' Blue Origin has developed its BE-4 engine to power an orbital delivery system, and they have the US Air Force on board. Not to be left out of the market, Virgin has also developed a small payload orbital system, Virgin Orbit with its Launcher 1. Flown to 35,000 feet, slung beneath Cosmic Girl, a Virgin 747, the 2-stage rocket can lift up to 500 kilograms into orbit and an inclination up to 120 degrees. Dream Chaser is still in the running with its pilotless shuttle, still under development for long-duration orbits. The late Microsoft founder Paul Allen's company Stratolaunch has unveiled the largest aircraft in the world, a scaled-up airborne launch platform with multiple payloads from the existing Pegasus rocket to a medium and heavy launch vehicle and a reusable spaceplane in the future. In the meantime, there is no shortage of conventional launch systems competing for their share of the market. From the USA, Europe, China, India, Japan, even Israel and New Zealand. key to any launch system is, of course, the engine. The smaller, lighter, and more powerful, the better. They pose many design problems. Fuel type, reignitable, chamber pressure limits, sea level or vacuum exhaust nozzle shape, but above all, reliability and cost. This is the Avio rocket factory in Colleferro, Italy. Here, engineers are developing the carbon fiber casing for the solid propellant rocket stages of ESA's new Vega C launcher. To build them, 5,000 kilometers of carbon fiber impregnated with epoxy resin is wound around a pre-made metal mandrel. This produces the very lightweight but sturdy casings for the first, second, and third stages of the Vega launcher. These casings are later fitted with an engine and loaded with solid propellant. One of these solid propulsion engines is the P120C. It was recently successfully tested in Kourou and is the largest and most powerful monolithic solid propulsion rocket ever built. With its new rocket, ESA hopes to respond to launcher market demands. The agency is also looking for value for money. This new engine is designed with the latest immersive technology and leading-edge materials and processes. Mass production will bring down the unit cost, but the design is for both Vega C and the strap-on boosters for Ariane 6.
So certainly in the launcher sector, the competition is growing worldwide. But we believe that the European answer, the ESA answer with Vega C and Ariane 6 is the right answer. In an aggressive manner, we are trying to make things more and more competitive. One of these examples is the joint solid rocket motor that we are developing across the two programs, the Vega C and the Ariane 6, the P120C solid rocket motor that enables the possibility to harmonize resources and to have the same motor serving the Vega C as a first stage as well as the Ariane 6 in both configuration as a strap-on boosters. So this is a very good answer to tackle the competitiveness aspect.
With Vega C, the C stands for consolidation, ESA is further developing Vega. It will add increased performance to the flexibility of the current system without increasing the costs. Today, Vega can launch up to 1.5 tons on a 700-kilometer orbit. With Vega C, it will go up to 2.3 tons. In order to increase performance, two new solid propulsion engines have been developed, the P120C and the Zefiro 40 for the second stage.
It is clear that whatever we develop has an exploitation objective. So we do not develop rockets just for the fun of it, but we develop rockets that need to be exploitable, therefore competitive in the worldwide market. And that's the way we are working hand in hand with industry to prepare them to walk on their legs in the future throughout the exploitation phase.
Further enhancements are made with Avom Plus, which is derived from the current Vega's Avom upper stage. Investing in new rocket motors also means investing in new launch facilities.
We have foreseen a lot of activities to modify the launch site from the Vega configuration to the Vega C configuration. Vega C is a heavy, larger and length launchers with respect to the Vega one. So for this reason we have to modify the hatches to the stages, increasing the diameters for what concerns the first stage.
Other changes include modified fluid services and installation of a more powerful crane needed to lift the heavier second stage of Vega C. During these modifications, the site has to remain operational for the scheduled Vega launches. In the end, the launch site will be compatible with both launchers. With Vega C, ESA is also working on related products such as the Space Rider, based on ESA's experimental re-entry vehicle IXV. It should allow for payloads to be sent into orbit and later return to Earth.
In addition to this, we have other products like a specific adapter for launching into orbit small spacecraft, so enabling the possibility of universities and research centers to access space at limited cost, so coping with the payloads which go from 1 kilogram up to 500 kilograms. We also have early elements of definition for a platform called Venus, which could allow payloads to transfer from orbit to orbit.
One unit which has been around for years and is still the Ferrari of rocket motors is the Space Shuttle main engine. Four of them will be mounted on the long-awaited Space Launch System. Reusing proven shuttle technology has saved time and money. The solid rocket boosters have been extended and tested. The Aerojet Rocketdyne RS-25 motors continue to roll off the assembly line. Fabrication of the immense components, cryogenic tanks, intertanks and fairings continues. The Orion capsule has flown once. The second flight-ready capsule is being prepared for the grand show. There is one more critical piece of kit required, perhaps one of the most important sections for keeping the astronauts alive, the service module. At Airbus in Europe, they have delivered the first flight-ready unit for the launch. The European component will house the electrical power, life support and propulsion unit for the Orion spacecraft, and like a giant pocket watch, every component is carefully and painstakingly assembled.
The European service module is part of an entire spacecraft built by an American company, Lockheed Martin, under the contract of NASA, and we are part of that. of that spacecraft NASA, Lockheed Martin is building, we are providing the European Service Module. We are providing the powerhouse of that entire spacecraft. That means we are providing the propulsion system, so the thrust to get into the dedicated orbit we would like to fly with the spacecraft. We are providing the air condition, I'm saying. That's the thermal control system of the entire spacecraft. We take care of the heat, which has been generated in the capsule, which has been generated out of several electronic components in the European Service Module as well. And we are making sure that that heat gets radiated into the outside of that spacecraft. On top of this, we are generating power. Our solar array wings are producing that power. We are conditioning that power and deliver that to the crew module and deliver that to the batteries which are located inside the crew module. And finally, we are also providing what the astronaut need to have to live in that spacecraft. That's mainly water in terms of the consumables, and that's oxygen and nitrogen to generate the atmosphere in the crew module itself. On the power side, we are proud that we have installed hardware which has already been flown several years ago on a shuttle. So the big engine we are flying here, the OMS-E, was a challenge for us to bring that into the vehicle. This is not new technology in that sense, but the integration itself, that was really for us a challenge that was new. We're preparing ourselves to be ready for the final integration with the rest of the vehicle, and then we are ready for a test campaign in the US, which is including several environmental tests, several functional tests. That lasts a couple of months, up to that point where the NASA team is handing over the spacecraft to GSDO, to the launch campaign, so that the vehicle can be put onto the launcher, and then we are ready for flight.
The first engine is the big engine, which is coming from the space shuttle. With this big engine, we perform the big transition maneuver to go to the moon or to go back to the Earth. So we can see here the auxiliary thruster, which are red. We have 8 of them coming from Aerojet. Here we have the OMS-E, so the main engine, but without the nozzle, which will be integrated in one of the latest integration steps. We can see here the propellant tanks. We have 4 of them, 2 for each propellant.
ATV, basically the automated transport vehicle here in Europe, played a significant role in terms of opening the door for that specific joint work on that spacecraft. It also played a role that we learned our lessons with a kind of that service module. Finally, the components we have flown on ATV, there are not so many which we carry on in the Orion European Service Module. We have a couple of them, mainly auxiliary thrusters, yes, on the RCS thrusters, and also a couple of tanks like our pressure tanks, but there are not just a few items which we carry on from ATV into the European Service Module design.
The difficulty here for the human spaceflight is the change of mindset. So to think that we are here in this space mission, we are flying human, and it's not like a rocket which is only flying with a satellite. Therefore, we are putting more effort on the safety aspect. We have a lot of redundancy. Each change we introduce, the smallest change we introduce in our system has to go through the safety boards, our safety board, ESA safety board, and then the program safety board, to be sure that we can bring the crew back home safe.
With Orion and the service module certified, the sky won't be the limit. We will see ships refueling in orbit, a gateway station with a return to the Moon, then on to Mars and beyond. Opening space to industry and exploration, spaceflight will become the norm rather than the exception. Mining and manufacturing in orbit, power production, and habitats. One day, it might be as easy as driving to work in that red convertible of yours.
New projects are advancing slowly, moving hardware into the testing phase, new designs, new capabilities. The next 12 months will see an intense rise in flight tests, demonstration launches and high-priority flights. Some are on time, others are not. Let's check the flight status of some of this new hardware and these new capabilities. Early morning at Armstrong Flight Research, Edwards, California. The Sierra Nevada Corporation's Dream Chaser sits engineless, awaiting a lift from a chopper. Lift and release. The remotely controlled lifting body makes an unpowered descent to the runway, completing another test run. The 10-year project has had its difficulties, but now the pilotless cargo ship is a step closer to a 2020 launch with cargo to the ISS. Boeing's crewed capsule, the CST-100 Starliner, has survived several high-altitude drops testing chute and airbag deployment. Weight and aerodynamic issues have pushed testing back by 8 months. Other aspects of design, however, are proceeding well, including new spacesuit designs.
We needed a suit that was airtight, could withstand the pressure differential, could get the crew down from an extremis situation, whether it was a fire or a cabin leak.
Underneath these shoulder covers is some material that we've developed that really helps provide pressurized mobility while still preserving unpressurized comfort.
You can pretty much lay there without any external cooling, right? It's that comfortable. It's something that I could stand here like this in and not have to worry about developing a big heat load.
The gas intake valves are located on the abdomen for easy access. The lightweight gloves and connections allow easier attachment and come with added technology.
A neat feature about these gloves is they have a advanced material here that enables you to interact with a capacitive touch screen. So any type of tablet you'll be able to interact with while wearing these gloves, well suited fully up in the suit.
The lightweight helmet, akin to the Russian Sokol design, is attached to the suit and sealed with a zipper. The suit is designed to be worn in the capsule and not for EVA purposes, and only comes in Boeing Blue. At the same time, Boeing has the capsule trainer in service, and NASA astronauts assigned to the commercial crew roster are getting a taste for the new capsule.
What the part task trainer does is it gives you a chance to get the feel and look, where to look, how to use the procedures. When you go to a screen in the background, when I hit this button, what's it going to look like?
So I think one of the greatest things about these trainers, it gets you so used to what you're going to do. You will practice a number of times that you'll be so familiar that, like a lot of people ask, is it scary? Of course it's scary because you're sitting on a rocket, but you're very familiar with where you are.
Test schedule calls for an uncrewed orbital test later in 2018 and a manned flight at the end of 2018. This is very ambitious, however, and previous experience of spacecraft engineering suggests it may be 12 to 24 months premature. Another company with an ambitious timetable is SpaceX, whose Dragon capsule is looking for an uncrewed flight early 2018 and a manned launch 4 months later. The new breed of entrepreneurial and commercial imperatives may just make it. The interior design of this capsule is more in line with high-end sports cars. Maximum use of carbon fiber, titanium, and other lightweight alloys, coupled with the latest in electronic display and glass control surfaces. Far more commercial in feel than the usual NASA or Russian practicality and minimal comfort ergonomics.
50 meters per second. Slightly below nominal. We're over 1 kilometer. Trunk deploy. Drugs look good. Sequencing the mains.
Their capsule is well along its testing phase, having completed both static and pad abort exercises, including parachute deployment test. A wild ride indeed. With room for a crew of 7, the Dragon capsule may well be the first commercial entity to launch and land astronauts from the ISS within a year. Unity spaceplane of Virgin Galactic has been building its test credentials slowly but steadily. Having suffered catastrophic failures in the past, they are fully focused on safety. Ground crew operations of both the spacecraft and its carrier plane are rehearsed ad infinitum, training and checking as flawless procedures evolve. Motor testing again and again. Unpowered flights, carried aloft by the White Knight 2. Rehearsing with ever greater complexity, the latest flights fully loaded with rocket motor and propellant tanks. The pilots performing a perfect landing. Next step, a powered suborbital flight, perhaps sometime in the next 12 months. The newest space-capable nation, New Zealand, is preparing the second launch of its Electron rocket. Powered by Rocket Lab's homegrown 3D-printed Rutherford engine, their second test launch is imminent, designed for the small satellites in low Earth orbit at a fraction of the standard cost. If this second test launch is successful, then Rocket Lab may drop the third and final test flight in favor of full commercial deployment next year. Blue Origin's reusable new Shepard rocket and capsule system has proceeded successfully through the testing phase, including launch, abort, and single parachute landings. It won't be long before 6 paying passengers will fly into space.
New Shepard has cleared the tower.
There it is, 70,000 pounds of thrust pushing that crew capsule.
Okay, so those 3 mains are reefed right now to keep them small. The reefing will remove shortly to fully expand, as you can see.
And touchdown of the New Shepard crew capsule.
Blue Origin is also developing a multi-stage version to reach orbit. The new Glenn could send payloads or passengers into orbit with a 2- or 3-stage variant, although it is still some years away. Delayed several times from an over-enthusiastic launch timeline, the Falcon Heavy will undergo a static fire test of all its 27 engines in the coming weeks. The first test flight will follow within the first 2 or 3 months of the new year. NASA's Space Launch System has hit further snags in development, namely issues with the welds of the enormous fuel tanks. Not unexpected, as the new technologies and manufacturing techniques evolve. Delays in delivering the Orion's EMS propulsion system have also set back the timetable, with 2020 likely to be the earliest a flight could take place. The James Webb Telescope has also been delayed by a year. A planned Ariane 5 launch will hopefully take place mid-2019. Ariane 5, Soyuz and Vega launches are due for an upgrade. At the European spaceport in Kourou, French Guiana, the new launch facilities for ESA's Ariane 6 launcher are being built. At least the big hole is there, the excavation is done, and the launch zone buildings will soon appear on schedule.
The independent access to space is, of course, the primary objective. And we always used European-developed launchers to fulfill this objective. We were lucky enough that we were very successful also on the commercial market with Ariane 5. We still have over 50% of the commercial market. As we all know, this environment is exposed to fierce competition. The offer of launch vehicles from 2020 onwards will be significantly higher. And we have designed Ariane 6. We have designed it to cost. We have designed it to be able to go against this fierce competition in 2020 onwards. And for this, of course, we also use this launcher to deploy European flagship programs like Galileo.
This move is associated with a change in the governance of the European launcher sector, based on a sharing of responsibility, cost and risk by ESA and private industry.
We are in the middle of the full development of the launcher Ariane 6 and of the base, which is ELA-4 in Kourou. I can say that currently everything goes well, it's on track. We are now in the situation where the configuration is clear. We know exactly what the configurations are with the Ariane 62 and the Ariane 64. The first one is for institutional payloads mainly because it's a single payload version where we can launch up to 4.5 tons in a sun-synchronous orbit. And the Ariane 64 enables a dual launch, which goes up to 10.5 tons in an equivalent geostationary transfer orbit.
ESA and its member states have a new role in Ariane 6 in the sense that we change governance. Governance by giving more responsibility to industry, to the private sector, while the public sector has defined the high-level requirements, which means that we said we want a cheaper launcher, we said we want an environmental friendly launcher, we want a flexible launcher, and this is absolutely key in the current situation to be ready to catch new markets, and Ariane 6 will be the right response to that. We can say that European industries are working full speed ahead. We just had maturity gate 6, what we call, where we can consolidate the industrial structure. We aim at starting the first batch of production next year, spring next year. So now we can say the industries are ready, they are full speed ahead, and we will start to produce Ariane 6 from next year onward. It is very clear, in a definition of a space power, the independent access to space is part of it. Ariane 6 and Vega C is the new family of the European independent access to space.
Vega C will cover the deployment of the Sentinel satellites for the EU's Copernicus program. Vega C will increase Vega's current capacity from 1.5 to 2.2 tons on polar orbit, which is the most common for observation satellites. For Ariane 6, the pad will be different from previous launches in Kourou, with a horizontal preparation of the stages. The first launch is still on target for sometime in 2020. Although there are extensive works going on at Kourou, they will not affect the upcoming Vega launch of the European Aeolus satellite, slated for early 2018. Next major launch is the TESS exoplanet survey mission. The satellite has completed pre-flight tests and is the first NASA astrophysics satellite to be launched under contract with SpaceX. The current launch window of the Falcon 9 is no earlier than March 2018 and not later than June 2018. The second exoplanet hunter, Cheops, is on schedule as well.
The satellite is commissioned by ESA. The project is being led by the University of Bern. They also built the instrument. That's the main part of the satellite. And the satellite structure, the platform with all the housekeeping, is built by Airbus in Madrid.
The satellite has gone through rigorous pre-flight tests, including vibration, acoustic and vacuum chamber tortures, and is on track for a late 2018 launch aboard a Soyuz launcher.
Gage du mauvais KM. Allumage triétage. À tous de DDO. Attention pour le décompte final. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Top. Et décollage VS12.
Bepi Colombo, the joint JAXA-ESA project bound for Mercury, is ready to launch. The mission consists of multiple parts, including the Mercury transfer module, a sun shield, and two scientific orbiters, ESA's Mercury planetary orbiter and JAXA's Mercury magnetospheric orbiter. The spacecraft was assembled in its launch configuration inside a clean room at the European Space Research and Technology Centre, or ESTEC, in Noordwijk, in the Netherlands. It has been dispatched to the spaceport in Kourou for its mid-2018 launch and 7-year flight to Mercury. Brute force at work. A European Ariane 5 rocket lifts off from Kourou. For Bepi Colombo, Europe's first mission to Mercury, the real journey has begun. Its 7.5-year flight is a major challenge in orbital mechanics and will see it reach the smallest and innermost planet in our solar system in 2025. There, its discovery mission will really begin.
A joint program with the Japanese space agency JAXA, Bepi Colombo is one of the most complex scientific missions ever launched. It carries 2 orbiters designed to unravel many of Mercury's mysteries. These include an unusual magnetic field, strange surface features called hollows, and ancient ice hidden in polar craters.
One spacecraft is provided by ESA, which is MPO, we call it MPO, Mercury Planetary Orbiter. And this spacecraft has a focus more on the planet. We want to observe the planet, do remote sensing, characterize the surface, count the craters, wanting to know about the composition of the surface, the interior of that planet. And in addition, we have a second spacecraft, and this spacecraft is called the Mercury Magnetospheric Orbiter, more focused on the environment, and this spacecraft is provided by the Japanese Space Agency.
We know the Mercury is very hot, and we have to make the satellite that can survive in that harsh environment. And we know, well, it is very difficult, and when we started, we already some development, and we think that we can do it. But actually, the hurdle is much harder than we expected, and takes a long time. But now, you see, this is a flight model.
Bepi Colombo's road, design, research and development phase, the construction, assembly and testing phase, has been long and hard, culminating in the launch from the European spaceport in French Guiana.
Mercury is 3 times closer to the Sun, and therefore the radiation or the heat which we are getting from Mercury is 10 times higher. So everything which we had to develop had to withstand the higher temperatures, but also the higher radiation doses which we got from the solar wind. And for that we need special insulation of our spacecraft, special materials to be developed for the antenna, for the solar panels. And that was a very big challenge for the mission in itself.
Now, of course, we do the health checks to verify the system is healthy. And we did alignment, mechanical checks, electrical checks all over. We checked the propulsion subsystems to see if the propulsion elements are still leak tight in preparation for the fueling.
Hardware apart, training of the scientists and technicians back on Earth was extensive, requiring years of preparation.
The simulations campaign is the first time that all the experts involved in the Bepi Colombo spacecraft design, integration, testing and operations work together as a single team. The campaign is essential for this group to learn to work as a single team, to train the decision-making process. The campaign is also very important for us to fine-tune our plans and procedures. It's the first time that we exercise the flight plans and procedures in a realistic context, taking into account communication constraints, ground station, and timing.
In preparing for a mission like this, we have to carefully train all the aspects. What we actually do in the rehearsal, we do in preparation of a launch, we train the teams to work together, we train the teams to work with the flight procedures, and also we train the teams as much as we can in flight conditions. So normally when we test before, we test with many workarounds. What we try to simulate here is actually to replicate as much as possible flight condition, and we typically do between 20 and 30 of these rehearsals before a flight.
With the nail-biting launch sequence complete, for many it's time to sit back and wait.
The cruise will be a bit above 7 years. We will fly by once the Earth, 2 times Venus, and 6 times Mercury itself, before we come into the orbit, which allows us to capture with the small gravity of planet Mercury against the big sun. That means when we fly, we constantly brake against the sun because we fly into the inner side of our solar system. Yeah, and when you fly towards the most heaviest element there, you constantly accelerate. We don't want that. That's why we decelerate.
Because this planet is so close to the sun, you need to have a lot of energy to go there. It's even easier to send a spacecraft to Pluto than to Mercury. You have to brake until the gravity of the sun, and you need a lot of energy. And for that reason, our mission takes quite a long time, because we also need the help of planetary flybys in order to bring our spacecraft there. Then we want to send 2 spacecraft in an orbit around Mercury, and that in itself is also a problem, because on the other hand you need to brake against the sun, but on the other hand you also need to accelerate your spacecraft to bring it in the same speed as Mercury goes around the sun, and then to finally drop it into an orbit of the planet. I'm working now 14 years on this mission, so it's really like a baby growing up and then leaving the house finally. So for me, it's a special moment.
Bepi Colombo's main component parts are 2 orbiters and 1 transfer module. These took 4 weeks to disassemble and pack, and required 70 shipping containers and 4 cargo planes to ensure safe delivery to the European spaceport at Kourou. Spacecraft have got up close and personal with Mercury twice before, thanks to NASA's Mariner 10 probe and, some 40 years later, the Messenger mission. Messenger mapped the surface and identified strong evidence for water ice in shaded craters. But its mission also raised new questions about this mysterious planet. This latest probe has a sophisticated suite of sensors and instruments that will come into play when it reaches orbit around Mercury.
So the big step forward for Bepi Colombo is the fact that we have 2 spacecraft, the European Space Agency spacecraft, which is looking directly designed to look at the surface of the planet and to study the planet in detail. And the orbit is designed such that you maximise the objectives that you can do relating to the surface. And the second spacecraft is designed to look at the environment. And so having 2 spacecraft will enable us to do a great deal of new science compared to the previous missions.
With Bepi Colombo, with a 2-satellite approach, we have 1 satellite, the MMO, sitting in the solar wind, and the other one is inside the magnetosphere, so we can see what is coming towards the magnetosphere and what is driving changes within the magnetosphere.
We have 11 instruments on board the spacecraft, and when we are at Mercury, these instruments are gathering data, and then they will store it in effectively a large hard drive, which we have on board the spacecraft. That data is then collected over a number of hours, and when we have a visibility with the spacecraft in Mercury, typically it's every 16 hours we can talk to the spacecraft at Mercury. The data is then downlinked using a very large high-gain antenna. It's a very powerful antenna in order to have a data rate of about 340 kilobits per second. If you compare it to your home internet, this is nothing. It's a very slow data rate, but it's very fast considering we are very close to the sun and we might get some interference from the energy from the sun. So it's as powerful as we can have with the resources we have on board the spacecraft.
With the assistance of gravity flybys, the spacecraft will rely on its solar electric propulsion system. It consists of 4 TX ion thrusters, fueled with xenon gas that is ionized and electrically propelled out, providing thrust for months at a time. The thrusters will rely on the spacecraft's solar arrays for power. The T6 thrusters can accelerate Bepi Colombo 15 times more efficiently than a conventional chemical thruster.
So at Earth, the solar flux is 1.4, more or less 1.4 kilowatts per square meter. As we approach Mercury, which is the innermost planet of the solar system, that solar flux has risen 10 times. So now we have 14 kilowatts per square meter. Now you might think that's a good thing in the sense that it gives you more energy to turn into electricity to be able to run your thrusters. But it turns out that that immense flux that we're getting from the sun also drives the temperature of the spacecraft very high. And in particular, our solar arrays, which are sensitive to high temperature, need to be protected. Now, we do that in a number of different ways. We keep as much of the open surface covered in little mirrors that we call OSRs, optical surface reflectors, or with specially developed white coatings, which help to reject the heat from the sun. But perhaps the biggest mechanism that we use to keep the solar array cool is to off-point. Rather than pointing the solar rays directly to the sun, we point them at a very shallow angle. And what that does is it means it keeps the thermal energies under control while still giving us the necessary energy to turn into electric power for the thrusters. Now, the reason why the solar rays are so big is because we're off-pointing by so much that in order to get a sufficient cross-section of the solar array needs to be big.
Protected by multi-layered insulation, hand-stitched thermal blankets and a radiator to dissipate heat, ESA's Mercury planetary orbiter will have to cope with extreme environments.
If a unit is getting too hot, if one of the payloads is getting too hot, in order to stop that payload from being damaged, we'll switch it off. We'll send an emergency message back to the Earth, reporting that there's an issue. We need ESOC to take action to investigate why items are getting too hot, and then to recover the unit and the spacecraft.
Once they reach Mercury in late 2025, the orbiters will separate from the transfer module to begin their comprehensive scientific mission in 2026.
In principle, all the planets have the same chemical elements because the whole solar system has the same chemical composition, but it's distributed differently in different planets and different environments. So it's vital to understand what is the ratio of the abundances of different elements to understand the structure of the surface of Mercury.
One of the advanced sensors aboard Bepi Colombo is a sensitive imaging X-ray spectrometer called MIX, which produces a global map of Mercury's surface atomic composition at high spatial resolution.
The MIX instrument, the Mercury imaging X-ray spectrometer, looks at the fluorescence that happens when the sun shines on Mercury in X-rays. So it's a bit like when you wear a shirt in party lights which has been washed in the right sort of washing powder. The party lights shine on your shirt glows. And it's exactly the same with the sun and Mercury. The sun shines on the surface in X-rays, and the surface of Mercury glows in X-rays. And if you detect those X-rays, you can tell what Mercury is made of. And what it tells you, you're actually counting the atoms on the surface. So it tells you in a very quantitative way exactly what the surface layer of Mercury is made of.
So I would say one of the most exciting things about MIX is the fact that we will be able to produce the first images in X-ray wavelengths of Mercury's surface, and that is going to be able to give us a great deal of new information, both on a global scale and on a local scale, of how the composition of Mercury varies over its entirety of its surface. Another aspect of the MIX science, which I'm personally very excited about, is the fact that we can also see X-rays from the surface which are being produced by particles from Mercury's magnetosphere actually precipitating onto the surface and producing X-rays that we will be able to also measure. So we can have an extra aspect to the science that we can do relating to how Mercury's magnetosphere interacts with the surface.
Among the mysteries revealed by MESSENGER are irregularly shaped depressions known as hollows, found in clusters over a wide range of latitudes and longitudes. These hollows have bright interiors and halos with a fresh appearance that suggests they are geologically very young.
I think that there are two mysteries or two very intriguing objectives of Bepi Colombo. The first one are the hollows. The hollows are features discovered by MESSENGER. These features seem to be quite distributed all over the surface of Mercury, and is something related to the volatile that come to the surface after an impact, after a volcanic event. But of course we need Bepi Colombo to really characterize and to understand which is the origin of the hollows.
There are also clear traces of much more recent hollows where the surface has been eaten away by some process that removed solid volatile substances such as sulfur, chlorine, sodium and potassium as vapor.
And this is because we don't have the composition data. We can measure the dimension, the size of the hollows, we can have an idea of the distribution, but no more. And also, of course, MESSENGER didn't get so many high-resolution images, and didn't have the digital terrain model, the 3D images at high resolution, as we will provide with Symbiosis. In other words, I think that the hollows are one of the most interesting discoveries made by MESSENGER.
Existing evidence indicates that if combined and spread out over a city the size of, say, Washington, the amount of water ice concealed in Mercury's polar craters would be over 2 miles thick.
And the second point is the water, because even MESSENGER said, yes, on the polar region we may have some water ice hidden just in the shadow of the craters, because in the polar region there are some floor of the craters, some wall of the craters that are always in shadow, as occur on the Moon. But the MESSENGER didn't have the instrument to observe if it is, to make a direct measurement of water, as occurred on the Moon. And Bepi Colombo and Symbiosis will be able to do it with our spectrograph.
If confirmed by Bepi Colombo, the story of how the inner planets, including Earth, acquired water and some of the chemical building blocks for life becomes much clearer. It would support the theory that organic compounds as well as water were delivered from the outer solar system to the inner planets and may have led to prebiotic chemical synthesis and, as a consequence, life on Earth.
So studying Mercury is crucial to better understand the formation of our solar system, how Earth is formed and evolved, and where we are coming from. So Mercury is in a way a missing piece in the big puzzle of the formation of the solar system, and a crucial end member because it's close to the Sun And if you want to get this full picture, you have to look at the planet close to the Sun, as we also did in past missions that we were looking at the comets or planets further out.
We all have our individual science objectives for each of our instruments, and what we're starting to do now is to bring all of our ideas together, which obviously are complementary to each other, and we can start to form a broader set of goals at working group level, so the surface working group and the environment working group, and that helps us to again maximise the science that we can get from the mission by coordinating what it is that we want to do, potentially looking at specific targets on the surface and that kind of thing. We can work together to get the best from the mission that we possibly can.
ESA science and engineering teams have already been working on Bepi Colombo for more than a decade. But with a long journey ahead of it, the recent launch marks only the beginning of the next intriguing stage of Bepi Colombo's voyage of discovery.
For over 50 years, we have bombarded Mars with our probes and landers, spying from orbit to map the terrain, finding her strengths and weaknesses. On the surface, probing for her resources and learning of her defenses. The next generation of robots are readying to establish the beachhead. The time is approaching for the full-scale invasion of the planet, when humans walk on Mars and claim it for their own. The conquest of this enigmatic planet so far away has been both challenging and rewarding. ESA has delivered the latest conspirator, the ExoMars Trace Gas Orbiter, to search out the source of methane in the atmosphere. Its landing craft, the Schiaparelli lander, failed and crashed, yet another victim of Mars's defenses. The ExoMars orbiter, now captured by Mars's gravity, has begun the challenging process of adjusting to a circular orbit without fuel. This involved using the shifting Martian atmosphere to gradually slow the satellite in a process known as aerobraking.
With ExoMars, ESA is going to use for the first time a method called aerobraking for a spacecraft in orbit around Mars to decrease the orbit by letting it fly through the atmosphere and using the atmospheric density to slow it down instead of using fuel for the engines.
We have to take a lot of margin to be sure that even if we go through a moment where the atmosphere is more dense at the altitude where we are flying, we are still safe with the spacecraft.
That aerobraking process took more than a year to complete. It was complicated by the changing nature of the Martian atmosphere.
The Trace Gas Orbiter is really looking at active processes ongoing on Mars today, and life, present life, is one of the possible explanations. So it will be really a Sherlock Holmes work to try to put together a case for whether it's geological or biological activity that is responsible for the methane.
Meanwhile, plans are well advanced for the ExoMars 2020 mission, with the final design of the rover nearing completion. And scientists have shortlisted 2 possible landing sites to put it to use: Oxia Planum and Morth Vallis. Both are shortlisted because they have had an abundance of water in the planet's early history, the main building block for life.
First of all, we want a landing site that is ancient, because the hypothesis is that conditions on the surface of Mars 4.3 to 3.9 billion years ago were similar to those on Earth when life started here. So the site has to be old. The second condition is we want a site where we had liquid water present over hundreds of millions of years. And we want this liquid water to be what we call low energy or slow flowing water, like on the canals in Amsterdam.
The rover then scouts around for the ideal locations and, with its driller apparatus, digs deep into the earth to extract soil samples, which will be placed into its onboard chemical analysis equipment, hoping to find ancient signs of life. Beginning this year, the next wave of spacecraft begin their sojourn to the Red Planet. NASA's InSight mission, the first to be launched from Vandenberg Air Force Base in California for another planet, is preparing for liftoff. The vehicle had already been through its pre-flight test and had been shipped to the launch facility. It is crucial that all aspects of the lander are in perfect operational readiness. The probe is destined for the equatorial region of Mars and will look deep into the heart of the planet.
The InSight mission is a geophysical mission to Mars. It's going to go to Mars and take its vital signs. It's going to take its heartbeat, the seismic activity of the planet.
So we're going to be doing that using a seismometer, a very high-precision seismometer, using techniques that have been well developed on Earth to get the understanding of the crust, mantle, and core, and sort of the relationship between those.
It's going to take its temperature by measuring the thermal gradient of the surface, which tells how much heat is coming out.
We also have a heat flow probe, we call it HP cubed, and what that does is it's going to basically take the temperature of Mars, and from that it'll be able to understand what the thermal flux is over the course of a full Martian year.
And it's going to sort of measure its reflexes by looking at how the rotation wobbles with the tidal effects of the sun.
Our final experiment is called RISE, and that's going to be looking at the basically the wobble of Mars to help understand what the core size may be in composition.
InSight isn't just a Mars mission, it's really a mission to the terrestrial planet interiors.
So Mars is kind of the Goldilocks planets. It's not too big, it's not too small, it's just right. If it was too big, it would have retained a lot of activity and erased all the evidence that we're looking for. If it was too small, it never would have undergone the same processes that formed the Earth, and so it's really just right.
Mars will give us this insight into early planet formation and early planetary processes.
Understanding the details of the structure of the interior of Mars will allow us to address questions of planetary formation that we've only been able to guess at before.
We are missing cold, hard data, and this is what this mission will provide.
Meanwhile, NASA, ESA, and the Russians are continuing their programs. Soon, new missions from China, Japan, India, and the United Arab Emirates will begin. Getting humans to Mars is the pressing goal of NASA and other adventurous parties. Many big aerospace corporations contractors have all been at the drawing board working out the immense engineering and logistical challenges. They all concur that to get to Mars, you need more than a big rocket. NASA's SLS and Orion spacecraft are only two of many components that will be needed. With some more political emphasis, NASA, in concert with other agencies including ESA, Canada and the Russian space agencies, are able to push ahead with the Gateway Facility concept. Effectively building a space station in cislunar orbit between the Moon and Earth, it would be a staging post for a return to the Moon, the gathering of resources from the lunar surface, and an assembly point for a Mars flight and beyond. Orbital ATK is one of 6 companies selected for NASA's Next Step 2 program, a public-private partnership for commercial development of deep space exploration. Not the first to suggest the Moon be a staging post, Orbital ATK recommends a parking orbit in cislunar space built from its successful Cygnus cargo craft. First, they will launch an initial habitat module aboard NASA's heavy-lift SLS rocket with a crewed Orion capsule. Placed in a parking orbit, it will act as a platform for experiments and serve as a destination for future crewed missions. By 2025, additional modules would be added to the habitat, allowing deliveries of crew supplies and experiments, and serve as a waste disposal vehicle at the end of their missions. The modularity of the system also allows for multiple visiting vehicles, providing a base for lunar sorties. Mining for resources, in particular water, would allow for more cost-effective and longer duration missions to Mars. From water you gain hydrogen for fuel, oxygen as the oxidizer, and for breathing, and of course, drinking water.
We have places on Moon which are, at least especially at the South Pole, which has permanent darkness, where we can find water, and we know from some missions that there is water. Water is a good source to produce hydrogen and oxygen. And also to go into the shadow of the Moon, we will have places where we don't have the radiation coming from the Earth. So building a telescope over there by using the material we find on the Moon, so not bringing all the stuff from the Earth, that could also open new possibilities to look deep into our universe.
These crewed missions would also help with man's understanding of how we can best survive long-duration space exploration. By 2030, with additional modules, the habitat could be expanded to provide a Mars transit capability for demonstration expeditions lasting 1,000 days or more. Boeing, the primary contractor for the SLS rocket system, believe their plan will require 5 or 6 SLS launches to be able to get to Mars.
So we want to make sure that we've checked everything out and that we know that it's good to go before we actually leave for Mars. Because once we leave, we can't come back for over 2 years. And the reason for this is because it's the alignment of the planets. The way the planets revolve around the sun, it allows a window of opportunity to go from Earth to Mars basically every 2 years. Just to get to Mars, before you even land or anything, is going to take 7 or 8 months. The reality is you're going to be there for a year waiting until that window opens up to come back. And then it's going to take 7 or 8 months to come home.
Having a cislunar outpost enables international partnerships and commercial opportunities, such as exploration of the lunar surface and scientific and technological research. After cislunar space, we'll start the actual missions to Mars. The first mission will be to Mars orbit. This mission will teach us about the space systems that will take us to Mars and back. The next mission will send humans to the surface of Mars. The crews will undertake detailed scientific research and investigation. They will start to unlock the secrets of Mars.
Their initial concept, now under development, consists of a power and propulsion bus to provide electric power and propulsion, 2 habitat modules, an airlock module, and a logistic work module, then supplied by cargo and crewed modules from the US and Russia. And finally, it could be used as the vehicle and habitat for long-term exploration of space. Lockheed Martin's concept for transporting to Mars has resulted in a holistic view of the mission. They too will assemble the space gateway in cislunar orbit. This will provide the platform to build the Mars Space Base Camp and get it ready for flights to Mars. They see that Orion is a part of a larger system that provides the supplies and the scientific equipment needed for the journey. This resulted in what they are calling Mars Base Camp. Mars Base Camp is an orbiting mission with 4 main sections and 2 of almost everything for backup. Four large commercial solar arrays to generate electricity to power the spacecraft. For propulsion, we have 2 cryogenic stages, one either end, and 2 tank farms to store the fuel and oxidizer. Within those stacks lie 2 habitat modules and a large central living space to eat, sleep, and exercise. Most importantly, we have Orion. It is the command deck with all the avionics, navigation, and communications. Orion makes the spacecraft more reliable and gives the astronauts a safe ride home. The orbiting crew could also investigate the 2 moons of Mars, Phobos and Deimos, deploying landers or robots for sampling, even astronauts to explore the surfaces of these moons. The main mission, however, will, after careful examination, confirm a landing site for the next mission and the first human landing. From orbit, the astronaut scientists will have access to the entire planet's surface for rovers and drones to be able to make real-time decisions about where to go and what to examine, retrieving samples from the surface for study. Lockheed Martin's concept, the almost retro rocket ship, the MEDV Lander, is their design for a reusable launch and landing vehicle and is based on the current technology, including the Orion and shuttle systems, and not as far-fetched as first thought. Reusability and innovation will conquer Mars. Keeping costs down will make it viable, and making it doable is innovation. That's something that SpaceX is founded on. Their BFR is the direct Mars transport system, from liftoff on a reusable booster, a short time parked in low Earth orbit for a fuel top-up, then direct to Mars and a 3-month cruise, then landing directly on the surface of the red planet, ready to be refueled from local resources for the return journey, landing back on Earth in the one reusable spacecraft. In the meantime, SpaceX is testing its Falcon heavy rocket system in preparation for its maiden voyage. One of the issues of flights to Mars, which is addressed in part by the BFR, is the cruise time. In theory, SpaceX has it down to 3 months. The other NASA-led systems will take 7 to 8 months, a long time to house, feed and power a crew with little to do. Getting there much faster would be a game changer. One possible way to achieve this is nuclear power. Nuclear thermal propulsion, or NTP, could enable faster transit time both to Mars and beyond. NTP is powered by nuclear fission. How it works is conceptually simple. Energy from fission is used to heat a hydrogen propellant to about 2,420 degrees Celsius. This hydrogen is then accelerated through an exhaust nozzle, resulting in a propellant efficiency roughly twice that of the best chemical rocket engines. For example, it may be possible to fuel modern NTP systems with low-enriched uranium instead of highly enriched. The physical size of an NTP engine is largely determined by the rate at which fission energy can be transferred to the hydrogen propellant, but the equivalent volume of the uranium that would be split is actually quite small, roughly that of a toy marble. Getting travelers to Mars faster, NTP can take months off the trip compared to using traditional chemical systems. This would reduce the need for payload, food and power for the crew, minimizing the risks associated with exposure to galactic cosmic radiation, microgravity, and other hazards of deep space travel. The maturation of nuclear thermal propulsion will also promote the successful development of the kilopower fission power systems for use on the Moon, Mars and other destinations, as a main source in situ for life support, communication, industrial and other diverse applications. Harnessing first-generation NTP systems is a first step towards advanced nuclear propulsion systems capable of travel throughout the solar system.
The building blocks of the solar system are quickly giving up their secrets. 2 major missions are underway. The NASA OSIRIS-REx, which is now closing in on its target asteroid Bennu, and the JAXA mission Hyabusa 2 to Ryugu, which is well into its observation leg of the mission, studying the asteroid up close. Both missions hope to return samples to Earth for more complete study. A 3.5-year journey to asteroid Ryugu is over, and the Hyabusa 2 science mission begins. Ryugu, part of the Apollo group, is potentially a threat to Earth in the years to come. It's an unusual asteroid, a CG type, meaning it has qualities of both C-type and G-type carbonaceous asteroids. It is just under a kilometer in diameter and fast-moving. As part of its payload, Hyabusa 2 has several deployable landers, 2 Minerva IIs, the Franco-German mascot lander, and target acquisition markers for the touchdown.
Okay, we want to see the boulders. We have a chance to see the boulders in a vertical structure. We also see the crack in the boulders. There is also regolith. We know from the spectral information we have so far that there is something a little bit redder, something a little bit bluer on the surface. So that's very interesting because there are differences on the surface. We have the feeling that the bluer, it may be a little bit fresher than redder. And that basically gives us a good idea of the history of the material on the surface. And of course, there are a number of landing sites which are red and blue, or which have red and blue in it. And that's probably preferred, at least for the camera, so we have a chance to see both of the surface units.
From the feedback I have obtained now from our principal investigators of the instruments seems to be that it's a very interesting asteroid and that there are several aspects which is covering the science objective of each instrument.
First to be deployed to the asteroid were 2 Minerva probes. These rovers are based on the original Minerva craft flown on Hyabusa 1, which unfortunately failed to land on their target asteroid. These ones, however, were successful. They have radioed back several stunning photographs from the surface of the asteroid, including this sequence of the Sun crossing the skyline as the asteroid tumbles.
Asteroid missions are very important and very interesting from the scientific point of view because it is believed that asteroids and comets are bringing water to the Earth in the very early phase of the development of the Earth. And with this water and also organic materials, it is believed that life on Earth has developed. And very importantly is also there to understand the evolution of the solar system, because asteroids are supposed to be building blocks of our early solar system.
The Hyabusa 2 mission has been years in the making. As with any deep space probe, years are spent on the drawing board developing the hardware and software. Then come years of construction and extensive testing. The aim of the Hyabusa 2 mission is to learn more about the origin and evolution of the solar system. As asteroids account for some of the most primordial celestial bodies, researching them gives us a glimpse into our cosmic past. Scientists are keen to learn more about the properties and structure of near-Earth asteroids in order to gain new insights into how our solar system formed and how water and life emerged on Earth. It's an audacious mission.
I mean, they're flying to an asteroid. Now we map the asteroid, then a lander will be deployed like Mascot or Minerva. They're trying to do 3 samples, and then they have also explosive on board to produce a crater on the surface of in the asteroid. I mean, this is, to me, it's a unique mission they are doing, and we are part of it, so I'm really proud of it.
And of course, we are interested in the geology, the geomorphology, the structure, the size of the big boulders, and also the structure of the regolith, and giving some hints of the evolution of the surface, of the forming and evolution of the surface of Ryugu. Oh, I think for a camera, all of the rendering sites are quite okay. So the most interesting thing is to see the big boulders from the vertical structure. We really can look how deep they are in the surface. And there are many boulders on Ryugu, so I'm pretty sure we get a good view of this interesting part of this asteroid.
The second batch of asteroid landers developed by the German and French space organizations were launched and, after a short freefall, successfully landed at the southern hemisphere of asteroid Ryugu. After bouncing several times on the rock-strewn surface, the 2 landers have begun their scientific research.
And you know that Mascot is made to bounce. That makes it robust, but it also means that the final resting location is not exactly possible to calculate it. So there's a dispersion of possible sites, and there is some variation in between. There could be, among these many possibilities, some bad ones, and we have to go to places where the chance to hit a good one is highest, but does not exclude that we end up in a bad one.
Autonomous handling doesn't mean that Mascot is doing everything as he likes to, so there's lots of sequences and command stacks behind, which are carefully tested and planned. So the robustness of these sequences have to be tested against all these different conditions we can meet on the asteroid. So if we bounce or land more in the west or more in the east, for this, the input Mascot has, which he uses for his autonomously, this is really carefully planned and tested, and so there's all the work in, and I think we did a very well job, and so I'm relaxed.
With its 4 instruments, including the Micromica spectrometer developed by the IAS Space Astrophysics Institute at Orsay with CNES oversight, Mascot is set to analyze the mineral composition of grains in the asteroid's soil in an attempt to unlock its secrets at 2 sites just a few meters apart. They also took some fascinating images.
I think at least for me, the most important question is the big number of boulders. Where did they come from? Why has this asteroid so many boulders? Why are these boulders to some extent covered by the surface, so they are in the subsurface? And the question here is, what are the source of the boulders? Are they from the interior or coming from outside? Are they a relic from some kind of collision from a bigger body, where Ryugu is now a relictic part of it? So I think that's the most important question.
Mascot was operational for over 17 hours, during which it collected data from the asteroid's surface and transmitted it back to Hyabusa 2 overhead, which relayed the data back to Earth. The next probe to be released is the 3rd Minerva robot, the largest of the Minervas.
I would like just to express again this amazing work which the whole team has done, DLR as well as CNES, as well as JAXA, surely. This was a very good example of a very good collaboration on an international level, and I hope that it will go on in the future.
GNC that has to tell the autonomy manager if we are on the right side or which side we should turn to uprightly.
For France, this was a big expectation.
The entire mission has been a close collaboration between nations. Japanese, German and French scientists and engineers have enjoyed over a decade of scientific cooperation, even if there are language barriers.
Realistic delivery with 6 slots in which the mascot...
I like it because it's a small mission with little overhead, and it's very nice to work with the Japanese because they are very success-oriented. They are willing to take risks. They have also, because of language issues, much less paperwork than NASA or ESA does. So most things are done in discussions, and you agree on something. You look into your eyes and say, yes, we do this, yes. And you rely on the words. You don't sign big papers. And that's something I like because it makes work so much easier and smoother and quicker.
Oh yes, the mission is very good. There are, in all the teams from Hyabusa mascot, there are very excellent engineers and also very excellent scientists. So I'm really confident and excited. That's the first time we do this.
The Hyabusa 2 mission is very interesting from the point of view because Hyabusa 2 is investigating a C-type asteroid. Ryugu is a very primitive asteroid which is supposed to have organic material on the surface. In addition, Hyabusa 2 has got in situ signs provided by the Mascot lander and also 2 to 3 further small Minerva landers, and it will bring some samples back to Earth so that we can investigate it then on Earth in the labs.
In the spirit of friendly competition, NASA was quick to congratulate JAXA for reaching their asteroid first.
This is Dante Loretta, leader of the NASA OSIRIS-REx asteroid sample return mission, congratulating you on the successful approach to asteroid Ryugu. We're all very proud of your amazing accomplishments so far, and we look forward to working with you together over the next year to maximize the scientific return from our 2 missions.
NASA's OSIRIS-REx probe is about to reach its target, Bennu, another CG-type asteroid close to Earth's orbit. A less ambitious mission, OSIRIS-REx will touch down and retrieve a surface sample, then return it to Earth.
Oh, asteroids are very interesting objects. So they are very primary. They are the fundamental things, the fundamental material of the solar system. And on the other hand, they have, to some extent, they cross the orbit of the Earth. They are dangerous. And just to know their structure, composition will help in order to avoid collision with the Earth if this may happen. And that will give us enough information in order to really find a way to mitigate this kind of catastrophic future.
And there is no shortage of conceivably dangerous asteroids out there.
It's one of the main points, of course, yeah, because we really cannot exclude it, but it's on a long time scale. But in any case, we know from the past, and we know from the past 4 billion years, that this is a real danger for planets.
"66 million years ago, one asteroid measuring 10 kilometers across completely changed Earth's climate, wiping out 2/3 of living species and consigning the dinosaurs to history books and museum displays. Fortunately, large asteroid strikes are very rare, but smaller ones can still be dangerous. Along with other organizations across the world, ESA is working hard to identify and track them.
We currently have a detection rate of something like 200 asteroids per month, and maybe 3, 4, 5 of them are objects which might hit the Earth. So currently we have 740 objects where we don't know if they will hit the Earth or not. There's none which is really a serious threat, which we currently know of. There's plenty of things out there which we have not yet detected, which we are still searching for, but from what we know right now, there's nothing which we have to really worry about. What we are worried is if a 20-meter object would approach. That was the case 5 years ago in Chelyabinsk, when a 20-meter object exploded over a city in Russia, and 1,500 people went to hospital because they were close to a window or they were hit by fragments, and they were not aware, nobody knew that this object would come. And this is what we could improve in the future, that our telescope would detect this a week maybe in advance.
ESA's new Fly-Eye telescope will conduct automated nightly sky surveys. It works by splitting the image into 16 smaller sub-images, greatly expanding the field of view.
We plan our Fly-Eye telescope in Sicily. We can scan the sky within 48 hours. So whenever an object bigger than 10-15 meters would approach, we should be able to see it beforehand, and then we would pass this information to the authorities.
Currently, the first Fly-Eye telescope is foreseen to be placed in Sicily, near the Monte Mufara. There are other 3 telescopes foreseen in the frame of the next project, and there are many advantages in having 4 identical telescopes, both placed in northern and southern hemisphere. The coverage of the both hemispheres is due to geometric reason, in order to cover the full celestial sphere. Then, considering that the telescope needs a clear sky for the observation, doubling the number of telescopes allows to compensate in case of bad weather conditions.
ESA's Fly-Eye telescope will improve our chances of detecting these potentially dangerous objects, while the asteroid missions will increase our knowledge of asteroids and look at ways of protecting our planet. The telescope was designed and built by a consortium of companies from Italy, Poland, and Romania.
The Fly-Eye telescope is based on a novel and original optical architecture that mimics, as the name says, the eye of the insects. In practice, it is composed by 16 independent and single telescopes that share a common primary mirror. This way we can join together different optical features that are difficult to combine together in a single telescope. And every single optical channel, every single telescope that composes the Fly-Eye telescope is provided with a focal plane which already provides a large field of view. The combination of the 16 field of views creates a very huge field of view. In practice, we have for each single telescope 2.75 square degrees of field of view that multiplied by 16 gives the 44th field of view of the overall instrument. This is very important due to the fact that with such a large field of view you can map large areas of the sky very quickly, and you can this way scan the full visible sky at least 3 times per night. A typical observation of the telescope is about 60 seconds exposure time. During this time, of course, the structure must be very stiff in order to avoid the vibration that could blur the image and diminish the possibility of the telescope to look for faint objects. And this is very important from the optical point of view, due to the fact that all the performances that are collected together in the telescope must be maintained also from a mechanical point of view.
FlyEye telescope, due to its large field of view and also the capability to quick scan the sky, allow to arrive up to 3 complete scanning of the sky per night. This feature allows to implement what we call wide survey. What it exists today is what is called the deep survey, so a specific observation of an asteroid very far. But today we think we are the first, we are offering a service to cover all the world, because we can inform the population with a week in advance that an asteroid can hit to the Earth, so we can protect the population. This instrument can detect an object like a tennis ball at an orbit 1,000 kilometers, moving at 10 kilometers per second. After 10 detection, we can calculate the orbit with an accuracy of 20 meters along a track. So are important feature, and we can implement a really cooperative way between radar and optical.
ESA is currently working on a set of space safety and security activities, which focus on threats such as space weather, artificial debris, and asteroids. By enhancing the existing space situational awareness program, these will help us better understand the risks to our planet and prevent disaster.
Searching for asteroids and mitigating the risk of impacts, while at the same time collaborating with international partners. That's how I see how ESA can contribute to fulfill UN Sustainable Development Goals.
All going well, the Hyabusa 2 sample will land in the Australian outback sometime in 2020. OSIRIS-REx will follow with a sample for return in 2023.
The amazing Cassini spacecraft and its sibling lander Huygens have now concluded their scientific studies, bringing back years of data to be combed through by scientists, plotting their next journey to Saturn's space. Now it's time for other planets and other spacecraft to shine. Juno piercing the cloak of Jupiter, and her distant relative New Horizons at the edge of the solar system. After 20 years, the Cassini project finally comes to an end in dramatic style. But with one door closing, another opens. Now the enviable task of having to unravel the data Saturn has just laid bare begins. And they have literally just scratched the surface.
I think Cassini has left us with humankind's presence at another planet for 13 years, seeing things that we had never imagined seeing, and at the same time sharing that with the entire world and opening up vistas for the next sets of missions.
One of the issues facing scientists when looking at exploring the new frontier is leaving it in a better state than they found it. So, eliminating the problems of space junk or the introduction of alien microbes is paramount in their decision-making.
But it also helps us satisfy a planetary protection requirement. We're protecting the tiny moon Enceladus as well as Titan. Both of those have global oceans underneath their icy crusts, and just in case there might be life in those oceans, we don't want Cassini to crash into one of those moons once we're out of fuel.
While the main focus of the Cassini mission was to delve into the mysteries of Saturn and its rings, the moons of Saturn proved most science-worthy. And Saturn has many moons. In fact, 62 with confirmed orbits. Several are only 50 kilometers in diameter, the largest being Titan, which is bigger than Mercury. The Huygens module that traveled aboard Cassini also became the first probe to land on a moon other than our own and transmit data back to Earth.
The temperature at the surface of Titan is about minus 180 degrees, so it's very cold. The landscapes of Titan look a lot like those we have on Earth. We have rivers, lakes, seas, almost oceans of methane. It rains methane or a mix of ethane and methane, so there are lots of meteorological phenomena or geophysical phenomena on Titan that makes you think of what happens on Earth. But the ingredients are quite different.
But it is Saturn's sixth largest moon that excited many scientists, as it is virtually covered by clean ice and ejected plumes of water into space.
My favorite moon is Enceladus, and the reason I'm partial to Enceladus is it's the moon that my team discovered a water vapor plume at. But not only is there liquid water underneath the surface, but there's organic material, there's a heat source. You know, when people get excited about the potential for life elsewhere in the solar system, there are four things that you need. You need a heat source, you need liquid water, you need organic material, and you need those three things to be stable over some period of time so that life could potentially form. At Enceladus, we've got three. We're not sure about the stability over time yet. And so based on the Cassini observations we made back in 2005, we've had lots and lots more flybys of Enceladus. We now understand it much better. We understand what organic material is there. I mean, one of the instruments, the ion neutral mass spectrometer, in a very close flyby through the plume, found some ammonia in the plume.
First of all, we see plumes. Then we start finding out from the gravity measurements and the imaging that there's an ocean and that it's global. And then there was some measurements by the cosmic dust analyzer that suggested there was hot water being circulated through the rock, the silicon dioxide nanoparticles. This is just the final step that shows that there's molecular hydrogen being produced by these same hydrothermal processes, and that molecular hydrogen has the chemical energy to support microbial systems in the interior ocean.
It's really the longevity of the Cassini mission that's allowed us to put together the pieces of the puzzle to really understand a moon like Enceladus. And even this late in the mission, we continue to look at our data to better understand this ocean world.
Collating data is one thing, but interpreting and providing vision for future missions is another. This is an area for which the Cassini project came up trumps, because it not only brought together 3 agencies, it provided the ground for future scientists to develop skills that will provide the basis for new projects.
The number of PhDs we've put through the system that are going to be the educators of the next generations. We've put out 3,000 plus peer-reviewed papers, hundreds of PhDs, thousands of peer-reviewed papers. The legacy, the scientific legacy is huge. The engineering legacy, of using every ounce of engineering capability to exploit a system, I think is again, we will be built upon. And I can't ignore the international cooperation. I mean, we had 19 nations contributing hardware to this mission. We've got over 26 nations now contributing scientifically.
The mighty Jupiter is the current target under the microscope with the Juno mission in full swing. The story of our solar system is linked to Jupiter, as it is believed that it was the first planet formed. So if we can understand how, we can begin to unravel the origins of our solar system, and thus how the Earth came about. Juno must work in a very harsh environment to tease out the answers from the gas giant.
When you go to a place as hazardous as Jupiter, we put a lot of time through the whole development process in trying to design a spacecraft that will operate in the high radiation fields, the magnetic environment, the spacecraft charging environment, everything that you do with the Jupiter. And I have to say the spacecraft has been performing admirably.
Jupiter's radiation belts pose one of the biggest problems faced by Juno scientists. They exist within the enormous magnetic field that surrounds Jupiter, with its magnetosphere trapping and accelerating particles. It produces intense belts of radiation similar to Earth's Van Allen belts, but thousands of times stronger.
Juno just flew by Jupiter for the first time with all the science instruments on, and it was spectacular. The spacecraft performed flawlessly, the instruments all worked exactly as planned, and the data is amazing. We're looking deep into Jupiter, we're learning about the secrets that it's holding, but we're also getting a lot of surprises about the aurora, about the atmosphere, how it works. I mean, it's just incredible.
The flybys which followed showed that the massive amounts of energy swirling over Jupiter's polar regions were creating the giant planet's powerful auroras, but not in ways the researchers expected. What puzzled the researchers was the fact that despite the magnitude of these potentials at Jupiter, they are observed only sometimes, and are not the source of the most intense auroras as they are on Earth.
Juno had its camera, JunoCam, on during the flyby. We got the first pictures of Jupiter's poles, the North and South Pole. They were amazing, a lot of surprises in them. It didn't look like we thought, doesn't look much like Saturn's pole.
Jupiter's poles are covered in these cyclones and anticyclone storms, some of them half the size of the Earth or bigger. And we're puzzled as to how they could be formed and stable in that configuration. And the North Pole doesn't look like the South Pole. And so we're questioning, the scientists are really questioning whether this is a dynamic system and are we seeing just one stage and over the next year we're going to watch it disappear? Or is this a stable configuration and that these storms are circulating around each other?
While the polar activity appears unique to our solar system, the engineers are looking below its shell for answers.
The new science results from Juno really are our first look at close up at how Jupiter works. And so the first time we're looking inside of Jupiter with into the interior, and what we're seeing is that it doesn't work at all like we had predicted. Almost every model that has the interior motion, how the magnetic field, the gravity field, how the deep atmosphere works, it's all different.
Like most scientific undertakings, they result in more questions being asked than answered.
So Juno's original objectives really were to understand how Jupiter formed, and that would help us understand how planets general form and how the whole solar system was made. What we're finding is that actually we didn't understand giant planet dynamics very well, the whole atmosphere or interior structure.
What we've seen so far is exciting, no question about that. But it's like a puzzle.
And we're putting the pieces of the puzzle together, and it's exciting, but we don't have the whole picture yet.
And one of those puzzles is the so-called Great Red Spot. And while its presence in a turbulent gaseous planet is not unusual, the scale is. The red spot covers an area twice as large as Earth.
And we're going to go right over the Great Red Spot. And that's really going to be the first time that we get a close look at that and to see what it's like underneath the top surface layer. I mean, how deep are the roots to that? That's a 300-year-old storm. A lot of scientists believe that the roots must be very deep. Well, when we go over with our microwave radiometer, we're going to see, is it the same as the zones and belts, or is it very different? And nobody really knows.
But it's not just Jupiter's poles that hold the greatest interest for the Juno investigators. They are also intrigued by the weather pattern that is unique to this planet, yet familiar in other ways. Studying the atmospheric dynamics helps understand other planets' atmospheres.
So when we look at Jupiter, we see a lot of structure that looks very similar to the Earth. We can see storms, we see cyclones, we see anticyclones, and these sort of storms and weather systems that we see on Earth are very similar, and they're happening on Jupiter. Fluid mechanics is hopefully the same everywhere in the universe, but Jupiter and Earth are very different. Jupiter is much bigger, it rotates a lot faster, they're made of different material, and Jupiter's much further away from the sun than the Earth is. The quasi-biennial oscillation, or the QBO, on Earth is an equatorial phenomenon in the stratosphere where the winds are changing direction approximately every 2 years. Depending on which phase the QBO is in, eastward or westward, the temperature signal corresponds to that. So it's warmer in the eastward phase and cooler in the westward phase. It's been shown that it can actually be a barrier to transport of aerosols across the equator and has been linked to the frequency and the formation of hurricanes in the Atlantic and the Pacific Ocean. The long-term scales on Earth's climate is something that we're very interested in, and how that applies to other planets' atmospheres is really why we're studying Earth and Jupiter. The quasi-quadrennial oscillation in Jupiter's stratosphere is a temperature signal that we see in the equator, where we see the temperature get warmer and cooler approximately every 4 Earth years. We used a general circulation model where we focused on simulating the effects of small-scale waves produced from convection in Jupiter's equatorial region to simulate the QQO. The waves propagate upwards from the clouds and force the winds in the stratosphere to change direction, going from eastward to westward approximately every 4 years. Our model was able to reproduce the behavior of the QQO, but was also able to reproduce temperatures from the observations, and both of those together give us a lot of confidence that our model is very accurate in what's driving the QQO. The outer planets serve as a laboratory for understanding atmospheric physics under very different conditions that are present on the Earth. Understanding how their atmospheres change and evolve and their climates can give us insight into any planetary atmosphere.
Juno has studied the planet with a suite of tools, revealing much that was previously hidden to the human eye.
We have an infrared instrument on Juno called JURAM, and it was designed and built and delivered by the Italian Space Agency. And this instrument makes thermal maps of Jupiter. So the images are showing you what's warm, hot, cold on Jupiter. And one of the things you can see right away is the center of some of these hurricane-like storms are cooler than the surrounding area. And sometimes you go over a warm spot. And we went over one that was very small that seems hotter than the surrounding area. And that's very similar to what the Galileo probe went into back in 1995.
The Juno mission is unique because it's the first time that we've ever gone in a polar orbit, which goes from pole to pole, over the North Pole, through periapsis, and under the South Pole. All the other missions we've done and all the observations we made from Earth were made from the equator. And you don't see the poles very well if you're sitting on the equator. Yes, this is the first time we get the first clear, unobstructed view of what the aurora looks like and what the polar phenomena looks like. And at the same time, we're flying through the magnetosphere right above the aurora, so we can sample in situ the charged particles that are precipitating down magnetic field lines, the guys that are exciting the emissions that we see.
Juno, like its sister Cassini, has a use-by date when the craft runs out of maneuvering fuel. This may occur during its 12th orbit at the end of its prime mission. However, NASA may choose to extend the mission if there are sufficient reserves. In that case, the deorbit would occur later, on the 34th orbit, as part of the planetary protection policy of NASA. Its pathfinding mission is leading the way for the one to come, the Europa Clipper, a mission in the design phase to look closely at Europa, the moon with a hidden ocean, and the possible location for life to evolve beyond Earth. The blue haze of Pluto's atmosphere, possibly a hydrocarbon smog, seen from 200,000 kilometers away by NASA's departing New Horizons spacecraft. A few years ago, the dwarf planet Pluto and its 5 known moons were just small dots in the outer reaches of our solar system.
One of the important things you should understand about Pluto is the real scale of it compared to the rest of the solar system. So we've come to the beach to really convey that scale and distance. So if I draw the sun as a 30-centimeter circle, then we have to walk about 35 steps this way in order to draw the Earth in the same type of scale. So we're walking the equivalent of 150 million kilometers, which we call 1 astronomical unit. Normally, Pluto orbits at about 40 astronomical units from the Sun, but it's actually quite an elliptical orbit, so it changes between about 30 and 50 astronomical units. But back to the Earth. So the Sun is over there at 30 centimeters, which means that the Earth should be about here, about 3 millimeters, something like this. If we were to draw Pluto in the same scale, it should be 0.3 millimeters, and it should be 1 kilometer down the beach. So I'm going to draw it. Now obviously I can't draw something that's 0.3 millimeters, so I have to draw Pluto a bit bigger. If this is Pluto, then its largest moon is Charon, which is about half its size. But Pluto has 4 other moons, Styx, Nix, Kerberos and Hydra. So there's a lot going on around the Pluto system. It's not just a cold, dead, icy rock.
The spacecraft spent 16 months sending its data back to Earth, and scientists and non-scientists alike have been enthralled by what it has revealed.
If you go in closer to the surface, you can see this type of really diverse terrain. So you have a very bright region. These are flat plains. Not entirely sure how they formed yet, but there's a couple of leading theories. There's a huge range of mountains. There's all kinds of different aged surfaces. Some of them have lots of craters. Some of them have very few, which means they're younger. If you look in a lot of detail at some of the mountainous regions, you can see that actually they're a few kilometers high, but they're made of water ice. I mean, on Pluto, it's so cold that water ice is the hardest thing. It's more like rock. And so the stuff that forms the softer material is actually nitrogen ice.
Water ice on Earth is close to 0 degrees, but on Pluto, it's minus 230 degrees Celsius. And there's a glacier of nitrogen ice, called Sputnik Planitia, thought to be under 1 million years old. This is young by planetary standards, and no one knows yet how it formed or is renewed.
One of the really fascinating things is some of the surface coloration you can see in these images actually shows that there are these compounds called tholins, which are a combination of elements, but they're related to prebiotic molecules, so they're kind of relevant to prebiotic chemistry. And I think the fact that they have been able to form on planetary surfaces very far out in the solar system at very cold temperatures really has implications for a lot of places. I mean, if you can imagine for star systems outside our own, where the star may be dim and the planets are quite far away, it's interesting to know that there are molecules that could be involved in supplying, biotic material to processes that, may one day lead to life or be involved in life or something like that. They're actually forming way out in the solar system where no one really expected.
Pluto is unlike anything seen before. But the 6 gigabytes of New Horizons images and scientific measurements are giving scientists mysteries to unravel for years to come. In the meantime, asleep for the moment, the probe travels deeper into the unknown, soon to awaken at its next destination.